When you look around the world, your eyes and your mind insist on showing you smoothness. A horizon stretches in an unbroken line. Rivers flow without interruption. Mountains rise with gentle curves, and the night sky seems to shine from a dome of continuous black velvet. Our senses evolved to paint reality as seamless. We see no gaps between grains of sand, no interruptions between notes of a song, no breaks in the fabric of a clear blue sky. The human mind feels at home in a universe that appears whole, where time runs as an unbroken melody and space lies as a vast, continuous stage upon which all events unfold. Classical thought reinforced this illusion. Euclid imagined geometry not as a collection of discrete points stitched together, but as endless lines that can be drawn forever, circles that can be divided without limit, and planes that extend without edge. To Euclid, the world was described by rules of eternal continuity. Centuries later, Isaac Newton gave physical weight to that intuition. In Newton's vision, the universe was a grand machine set upon a continuous stage of absolute space and time. Particles moved like clockwork, pushed and pulled by forces, yet always within that seamless background that never changed, never broke, never pixelated. Newton's mathematics reflected this, describing motions and trajectories as flowing smoothly through time, measurable to any desired precision. Space and time themselves were eternal canvases, untouched by the dramas they contained. Even when Albert Einstein reshaped this picture with his theories of relativity, he did not break the illusion. He revealed that space and time are not separate, but woven together into a single four-dimensional fabric. This fabric bends and curves in response to mass and energy, creating the dance of gravity. Planets trace their paths not because they are pulled by invisible strings, but because space-time itself bends, guiding their motion along natural curves. Yet despite this revolutionary shift, Einstein's space-time remained continuous. It could stretch, compress, and ripple, but never dissolve into separate pieces. It was like a sheet of rubber that could bend without tearing. Relativity shattered the Newtonian absolutes of time and simultaneity, but it left intact the idea that the fabric itself is smooth. And so, for centuries, our best theories agreed with our senses. Space was continuous, time was continuous, the universe was an unbroken expanse. But nature has a way of pulling the rug from under us, revealing that what feels obvious is sometimes only a shadow. The story of science is often the story of discovering that reality is stranger than intuition dares imagine. Light once seemed to move as a continuous wave, yet the discovery of quanta revealed it comes in indivisible packets called photons. Matter itself once seemed solid and continuous, yet atoms showed us that solidity is an illusion built from mostly empty space. Beneath the atom, we found electrons and quarks, indivisible units forming all known matter. Again and again, science has exposed hidden discreteness beneath what appeared smooth. Quantum mechanics in particular has shown us that continuity is fragile. Energy levels in atoms are not a sliding scale, but come in jumps, like rungs of a ladder. The electron cannot circle a nucleus at just any distance, only at specific ones. The act of measurement itself resists continuity, collapsing probabilities into definite outcomes. The mathematics of the quantum world is written not in unbroken lines, but in discrete steps and sharp boundaries. Continuity crumbles wherever quantum theory reigns. And this leaves us with a haunting question. If matter is quantized, and if energy is quantized, then why not space itself? Could the fabric of space-time, so seamless to our eyes and to Einstein's equations, actually be built from grains, pixels, atoms of geometry? The human imagination struggles to picture such an idea. We are so used to thinking of lines and surfaces as smooth that imagining a pixelated universe feels like trying to see the smallest brushstrokes on a canvas stretched across the sky. But if you look close enough at a painting, even the smoothest gradient is made of dots of pigment. Could space-time itself be like that, only appearing continuous from afar, but secretly composed of discrete quanta, too small for our instruments to glimpse. To find out, we must journey to scales so small that ordinary intuition collapses. There exists a limit, the Planck scale, far beyond the reach of microscopes, where distances are measured in 10 to the power of -35 meters. At this extreme frontier of physics, the smooth fabric of space-time may fray into something granular. But before we descend into that abyss, we must first understand why the illusion of continuity was so convincing, and why scientists now suspect that the very stage of the cosmos may be an elaborate mirage. The illusion of continuity has always given humans comfort, a reassurance that the world can be divided and subdivided without end, that between any 2 points there is always a middle, and between that middle too, more points still. It is the logic of the infinite, and philosophers used it as a proof that space and time must be continuous. The ancient paradoxes of Zeno rested on this very idea. How can an arrow in flight ever reach its target if it must first cross half the distance, and before that half of the half, and so on without end? The paradox only dissolves if we allow the arrow to traverse an infinite series of ever smaller divisions. Continuity was the answer, the assumption that the infinite is somehow stitched seamlessly together. Yet hidden inside Zeno's thought experiment lies another possibility, one almost never considered by the ancients. What if the divisions stop? What if there comes a smallest unit, an indivisible distance, a final grain of time, so that the arrow simply leaps across instead of moving through infinite cuts? That would mean the arrow's motion is not continuous but pixelated, and our smooth perception hides this leap. For thousands of years, such an idea would have sounded absurd. Mathematicians crafted entire systems on the certainty that space and time were continuous, while physicists built their theories on the same foundations. When the calculus of Newton and Leibniz was invented, it gave humanity an astonishing new tool, allowing us to describe motion and change as a flow through infinitely small steps. The planets could be predicted with precision, the tides explained, and projectiles guided, all thanks to the power of continuous mathematics. But calculus itself is a language, not necessarily a mirror of reality. It is a way of describing smooth change, not proof that nature is truly smooth. Like a map that represents terrain with elegant curves, calculus works as long as the terrain itself does not reveal too many jagged edges at small scales. Einstein's general relativity extended this language further, turning space and time into a fabric that could bend and stretch continuously. His field equations are written in the differential tongue of calculus, where changes are smooth and the geometry of the universe can be computed point by point. The success of this theory is undeniable, confirmed again and again by experiments, from the bending of starlight during an eclipse to the precise ticking of atomic clocks on satellites orbiting Earth. Yet the very reliance on smooth mathematics hints at the possibility of a hidden assumption. If the true structure of space-time were grainy, if it consisted of indivisible atoms of geometry, then general relativity might be like a fluid description of water. We treat water as continuous when we write equations for waves or currents, even though at the molecular level it is not continuous at all. Perhaps space-time is like that. Perhaps relativity is a marvelous approximation that works at scales where the atoms of space are far too small to be noticed. The emergence of quantum mechanics in the early 20th century made this suspicion stronger. The quantum revolution revealed that energy and matter, once thought continuous, come in quanta. The photoelectric effect proved that light cannot be absorbed in arbitrary amounts, but only in discrete packets. Atoms revealed electrons that occupy only specific orbits, not smooth gradients. Probability itself became quantized in the sense that outcomes snap into definite states rather than slide across continuous possibilities. Every discovery seemed to hammer the same lesson into human understanding. Continuity is an illusion. Nature is built from indivisible units. But there was one holdout, one element of the physical picture that resisted quantization: gravity. Unlike the other forces of nature, which submit to the rules of quantum field theory, gravity remains stubbornly classical. We can quantize light and electromagnetic waves, producing photons. We can quantize vibrations of atoms in a solid, producing phonons. But when we attempt to quantize the geometry of space-time itself, infinities erupt from the mathematics. The smooth fabric of Einstein resists being torn into discrete strands. It is as if space-time itself is whispering that it cannot be treated like the fields of particle physics, at least not without a deeper idea. This failure is telling. It suggests that the continuous picture we inherited from Euclid, Newton, and Einstein may itself be the obstacle. Perhaps gravity resists quantization because we insist on treating space-time as a smooth background. If instead we imagine space-time as fundamentally discrete, then the problem might transform. Instead of trying to quantize something continuous, we may discover that the geometry is already quantized at its core. In this view, continuity is only a large-scale mirage, like how a beach looks smooth from a distance, but reveals countless grains of sand up close. The grains of sand in this analogy would be the quanta of space-time itself. Philosophers have long pondered whether such a graininess might exist. Democritus in ancient Greece spoke of atoms, not only of matter, but of space itself. He imagined that both void and substance are made from indivisible units. For millennia, this idea was dismissed as speculation, while geometry and physics marched forward on the assumption of continuity. Yet now, standing at the edge of quantum theory and general relativity, Democritus begins to sound strangely modern. His intuition that space might have atoms may be closer to the truth than Newton's absolute space or Einstein's smooth fabric. As we peer deeper into the quantum world, the illusion of continuity grows weaker. Experiments in high-energy physics smash particles together with colossal force, probing smaller and smaller scales. Each time, we find new building blocks, yet no experiment has reached the scale where space-time itself might reveal its pixels. That boundary lies at the Planck length, unimaginably small, where the ordinary concepts of distance and time may cease to exist. It is at this edge that our theories break down, and where the question of continuity versus discreteness becomes unavoidable. The illusion of smoothness has carried us far, from the geometry of Euclid to the relativity of Einstein. It has guided explorers, engineers, and astronomers, offering equations that match observations with uncanny precision. But illusions, however useful, cannot be the final truth. If space is pixelated, then the very foundations of physics must be rewritten. The arrow of Zeno may not cross infinite divisions, but leap across indivisible steps of reality. The seamless sky may be a mosaic, its smoothness only an artifact of our limited resolution. And the fabric of space-time itself may be woven not from a continuous thread, but from discrete quanta, atoms of geometry waiting to be discovered. The illusion of continuity does more than soothe the human mind. It defines how we imagine reality itself. When you close your eyes and picture the universe, you probably see a boundless stage, smooth and seamless, stretching outward in every direction. This stage is so vast that it seems to have no edges, no pixels, no smallest part. It feels infinite, and in that infinity we place galaxies, stars, planets, and all the stories of life. Yet infinity is a treacherous companion in physics. Again and again, whenever theories encounter infinities, something fundamental is revealed to be incomplete. In Newtonian gravity, infinities appear at the center of point masses, and general relativity replaces them with curved space-time. In quantum mechanics, infinities erupt in raw calculations, and renormalization was invented to tame them. Infinity is rarely the final answer. More often, it is the signpost that our picture of reality is too simple, hiding a deeper truth. Consider the nature of measurement itself. With rulers, with clocks, with microscopes and telescopes, humans extend their senses across scales. The more precise our tools become, the more detailed our picture of reality grows. But precision has limits. In quantum mechanics, uncertainty sets a hard boundary. Try to pin down the position of an electron with perfect accuracy, and its momentum slips away into indeterminacy. Try to measure time with infinite precision, and the energy cost soars beyond control. At some point, attempting to divide space and time into smaller and smaller slices collides with the graininess of quantum theory. It is as if the universe refuses to let us look beyond a certain resolution, blurring the picture when we zoom in too far. If this is true, then continuity is not real but a useful approximation, like the illusion of motion in a film made from discrete frames. Even our senses play tricks that mirror this. When we listen to music, the notes feel continuous, flowing without interruption. Yet digital recordings prove otherwise. A song stored as digital data is sampled many thousands of times per second, and when played back, the ear perceives smoothness. The gaps between samples vanish into illusion. Could the cosmos be working in the same way? Could space-time be a grand symphony, sampled at unimaginably high frequency, playing back as seamless to our senses and our instruments? If so, then what we call continuity is a perceptual artifact, and reality beneath is built from indivisible steps. This idea challenges not only mathematics, but philosophy. If space and time have a smallest unit, then the infinite divisibility assumed by centuries of thinkers crumbles. Motion itself becomes a sequence of hops instead of a glide. Causality may need to be reinterpreted, because if events are separated by indivisible ticks of time, then between them, nothing happens. Our language strains to describe such a world, because every metaphor we have inherited presumes smoothness. We speak of flowing rivers, bending fabrics, and stretching lines. But if reality is grainy, then our metaphors are masks over a truth stranger than imagination. The very stage of existence may be a mosaic rather than a canvas. Science stands at the edge of this revelation. We know the mathematics of general relativity describes space-time as continuous, and we know quantum mechanics quantizes energy and matter. But the two pictures refuse to merge. At the boundary where gravity and quantum theory meet, the equations collapse into infinities, like a mirror shattering under pressure. That boundary is marked by the Planck scale, the realm of distances around 10 to the power of minus 35 meters, times around 10 to the power of minus 44 seconds, and energies so vast they lie beyond any machine humanity can hope to build today. At this scale, space-time as we know it may dissolve, replaced by atoms of geometry, by quanta of area and volume, by something so different from smooth fabric that even the word fabric no longer applies. To glimpse this frontier, scientists develop theories that abandon the assumption of continuity. Some envision space-time as woven from loops, networks of connections where area and volume are quantized, much like pixels on a cosmic screen. Others imagine strings vibrating in many dimensions, from which space-time itself emerges as an echo. Still others picture a froth of foam, where space-time bubbles and seethes with uncertainty. Each of these ideas is a rebellion against the illusion of smoothness, a search for the grain of the universe. Yet so far, the illusion holds. Every experiment we have run, every photon observed from distant galaxies, every ripple of space-time caught by detectors, still paints a picture of smooth continuity. The cosmos hides its pixels well, if they exist at all. But the pressure builds, because theory insists the illusion cannot be perfect. Somewhere, at some scale, the disguise must fail. And when it does, we will see the universe not as an unbroken stage, but as a mosaic of quanta, each one a tile in the great design. As we stand at this threshold, the question becomes urgent. Is reality continuous, or is it grainy at the core? The answer will reshape our understanding of space, time, and existence itself. For now, we live in the illusion, walking across what seems a seamless floor, gazing into what seems a seamless sky. But the next chapters of this story will take us deeper, past the comfort of smoothness, down to the Planck scale where the illusion may dissolve, and where the true structure of reality begins to reveal itself. The illusion of smoothness carries us far, but it cannot carry us across the final frontier of knowledge. When the forces of nature are gathered together on the stage of physics, three of them play well under the rules of quantum mechanics. The electromagnetic force, which governs light and electricity, submits to quantization and reveals the photon. The weak nuclear force, which allows particles to decay, submits as well and yields its own quanta. The strong nuclear force, which binds quarks inside protons and neutrons, also yields, its gluons stitching the particles together. All three forces are tamed within quantum field theory, a framework that describes them with staggering accuracy. This framework allows predictions so precise that measurements of the electron's magnetic moment agree with theory to more decimal places than any other scientific calculation in history. It is a triumph of human thought. Yet one force refuses to join the company: gravity. Gravity is the most familiar of all forces, pulling apples to the ground and guiding the planets around the sun. It sculpts galaxies and shapes the large-scale architecture of the cosmos. But when physicists attempt to quantize it in the same way as the other forces, the mathematics breaks apart. The infinities that appear cannot be renormalized away. They multiply until the theory collapses. Quantum field theory, so successful elsewhere, cannot contain gravity. It is like a language that suddenly falters, unable to describe one essential part of reality. This failure is not a small blemish. It is a deep wound in the body of physics, a sign that something fundamental is missing. The reason lies in the nature of space-time itself. The other forces operate within space-time. Their particles dance upon the stage, interacting with one another according to quantum rules. Gravity, however, is the stage. In Einstein's theory, gravity is not a force transmitted by a field laid upon space-time. It is space-time. Mass and energy curve the geometry, and objects move along the curves. To quantize gravity is therefore to quantize space-time itself, to replace the smooth background with something grainy. This task has resisted every attempt, not because the mathematics is weak, but because the very assumptions of smoothness might be false. Trying to quantize a continuous fabric may be like trying to slice fog with a blade. If the fabric is already granular, then our approach must change entirely. The stakes are enormous. Without a quantum theory of gravity, physics remains incomplete. At everyday scales, Newton's and Einstein's descriptions suffice. At atomic scales, quantum mechanics rules. But at the boundaries where both must apply, such as inside black holes or at the birth of the universe, the theories collide violently. Relativity predicts smooth curvature leading to singularities of infinite density, while quantum mechanics forbids infinities, demanding discreteness. The two theories scream different answers to the same questions, and neither can silence the other. To move forward, we need a deeper synthesis, a framework that includes both. That framework is called quantum gravity. But quantum gravity is not simply a unification of equations. It is an attempt to answer whether space and time themselves are fundamental or emergent. If space-time is continuous, then perhaps it can be quantized like any other field, yielding a particle called the graviton, a quantum of gravity moving through a smooth background. If space-time is not continuous, then gravitons may only be approximations, and the true theory will describe atoms of geometry themselves, entities more fundamental than points and lines. Either way, the pursuit of quantum gravity demands that we confront the deepest assumptions of physics, stripping away the illusion of continuity and asking whether the stage of the universe is itself a player. The search has been long and filled with dead ends. Early attempts treated gravity as a field like electromagnetism, writing down Feynman diagrams where gravitons exchanged between particles carried the force. But as calculations stacked, the infinities multiplied without control. Renormalization, the trick that works for the other forces, failed. This was a signal that gravity cannot simply be shoehorned into the same framework. It demands a new principle. That principle, many suspect, is the recognition that space-time is not continuous at all, but discrete at the Planck scale. If matter and energy come in indivisible quanta, perhaps space-time must as well. And so, the quest for quantum gravity became more than a technical project. It became a philosophical journey. What is space? What is time? Are they fundamental ingredients of reality, or emergent patterns like the smoothness of water that hides its molecules? Could causality itself, the order of before and after, dissolve at the Planck scale? To answer these questions requires new mathematics, new experiments, and new imagination. It requires daring to think that the universe's most obvious features are illusions, that smoothness, continuity, and flow may all be masks hiding a pixelated truth. The road ahead is treacherous. Experiments cannot easily probe the Planck scale, for it lies beyond reach by many orders of magnitude. The most powerful particle colliders on Earth fall short by factors so vast they might as well be insurmountable mountains. Directly smashing particles together at Planck energies would require a machine larger than the solar system itself. Yet physics has always triumphed, not by direct reach alone, but by inference. Just as atoms were inferred before they were seen, and quarks inferred before they were confirmed, so too the quanta of space-time may be inferred from clever experiments and careful reasoning. The quest for quantum gravity is thus both a scientific expedition and a philosophical voyage, a pursuit of the most elusive truth of all, the nature of reality's stage. The puzzle of gravity within the quantum world grows sharper the closer we look. At ordinary scales, Einstein's general relativity and quantum mechanics live in separate realms, rarely interfering. The orbit of Earth around the Sun does not need quantum corrections, and the energy levels of an atom do not need relativity to be understood. But there are domains where the separation collapses. Black holes are one such place. Inside them, the density of matter grows so immense that relativity insists space-time curves infinitely. Yet quantum mechanics forbids infinite values, insisting that discreteness must intervene. Another domain is the birth of the universe. The Big Bang is described in relativity as a singularity, a point where the density of energy is infinite and the equations break down. Quantum theory, however, whispers that such a singularity may be a mirage, that at scales near the Planck length, space-time cannot shrink smoothly to nothing, but must dissolve into something else. These contradictions demand resolution. They demand a new framework in which gravity and quantum rules are not enemies but partners. The attempt to craft such a framework has drawn some of the brightest minds of the last century. Richard Feynman himself once tried to quantize gravity using his diagrams of particle interactions, treating gravitons as carriers of the force. But his calculations, though elegant, exploded into uncontrollable infinities. Freeman Dyson, another towering figure, concluded that perturbative quantization of gravity would never succeed. Steven Weinberg explored the possibility of asymptotic safety, where gravity might behave in a controlled way at high energies, but this remains unproven. Again and again, the attempts reveal that gravity is unlike the other forces. It is not simply another actor on the stage, it is the stage itself, and that makes all the difference. The Planck scale emerges as the critical boundary in this story. It is defined not by human invention, but by the constants of nature themselves. Combine Planck's constant, the speed of light, and Newton's gravitational constant, and you obtain natural units of length, time, and energy. The Planck length is around 10 to the power of minus 35 meters. The Planck time is around 10 to the power of minus 44 seconds. The Planck energy is around 10 to the power of 19 giga-electron volts. These scales are unimaginably far beyond experiment, yet they mark the frontier where the smoothness of space-time is expected to collapse. They are the scales where a theory of quantum gravity must reveal itself, for below them, relativity and quantum mechanics both lose their grip. The analogy with matter is instructive. To the naked eye, water seems smooth, continuous, and flowing. But at the scale of molecules, that illusion breaks apart. Temperature, pressure, and viscosity are emergent properties of molecular motion, not fundamental entities themselves. If space-time is like water, then Einstein's curvature is an emergent property, and the molecules of space-time are the true reality. To find them is the goal of quantum gravity. And just as the atomic theory of matter resolved paradoxes in thermodynamics, so too an atomic theory of space-time may resolve the paradoxes of black holes and the Big Bang. Yet we must tread carefully. Nature has surprised us before with layers of structure more exotic than imagination. When atoms were discovered, they seemed indivisible. Then they revealed electrons, protons, and neutrons. Protons and neutrons, once thought fundamental, revealed quarks. Quarks themselves may yet reveal deeper constituents. Each time, what seemed continuous or indivisible proved otherwise. There is no guarantee that space-time will be different. It may be granular, or it may be emergent from something stranger still. Something that is not even spatial or temporal in any ordinary sense. In the quest for quantum gravity, we are not only asking whether space-time has atoms, but whether space-time itself is an illusion. The paradoxes of black holes sharpen this suspicion. According to relativity, a black hole is defined by its horizon, the boundary beyond which nothing escapes. But Stephen Hawking discovered that black holes radiate, emitting particles in a quantum process that slowly evaporates them. This radiation appears thermal, carrying no information about the matter that fell in. If that is true, then information is destroyed, violating one of the core principles of quantum mechanics. Relativity and quantum theory again clash, demanding reconciliation. Many physicists believe the resolution lies in the graininess of space-time, that the entropy of a black hole reflects the number of its microscopic space-time states. If so, then gravity itself is evidence that space-time is pixelated, though the pixels remain hidden from view. In the laboratories of thought, physicists explore radical ideas. Some imagine networks of loops that weave into spin networks, where space is composed of nodes and links, each carrying quantized area and volume. Others envision vibrating strings in higher dimensions, where space-time emerges as a hologram, a projection of a deeper reality. Still others picture space-time as frothing foam, bubbling with uncertainty at the smallest scales. Each approach is a step in the quest for quantum gravity, a different attempt to pierce the illusion of continuity and uncover the atoms of geometry. But none of these ideas have yet been proven. Experiments remain out of reach, and the mathematics is complex and incomplete. The quest is ongoing, a story still being written. What unites all these paths is the recognition that space-time cannot be treated as eternal, smooth, and absolute. The stage itself must be explained, not assumed. The quest for quantum gravity is therefore not merely a technical fix for infinities. It is a revolution in how we think of reality. It is the search for the architecture beneath the illusion, the scaffolding that holds up the universe we see. The search for quantum gravity is not only a technical necessity, it is also a profound challenge to human imagination. For centuries, space and time were the unquestioned backdrop of reality, the silent stage upon which matter and energy played their parts. Now we suspect that the stage itself is an actor, perhaps even the most fundamental actor of all. To quantize gravity is to remove the stage curtains and reveal what lies behind them. It is to ask whether the dimensions we take for granted are truly elemental, or whether they emerge from a deeper order, still hidden from our view. The paradoxes that push us toward this question grow sharper with every attempt to avoid them. The singularities predicted by relativity, points of infinite curvature where physics ends, are not acceptable final answers. They are warnings. They are like signs at the edge of a map, declaring "here be dragons," indicating that our theories cannot travel further. Infinity in physics is rarely a destination. It is more often a marker of ignorance, a symbol that our description has reached its breaking point. Quantum mechanics does not permit infinities in measurable quantities. It insists that energy comes in discrete steps, that probability resolves into definite outcomes. If relativity predicts infinities, then relativity must be incomplete. Quantum gravity is the cure to that incompleteness. And so, the idea of discreteness presses itself forward. If black hole entropy is finite, then the number of possible states of a black hole is finite. If the number of states is finite, then space-time itself cannot be continuous. It must be quantized into units of information, pixels of geometry. The holographic principle goes further, suggesting that all the information contained within a region of space can be described by bits written on its boundary, just as a hologram encodes 3 dimensions on a 2-dimensional surface. This is not just a hint of discreteness, it is a suggestion that space-time itself may be a construct, an emergent tapestry woven from information. In this vision, quantum gravity is not merely a merging of relativity and quantum mechanics, it is the revelation that space and time are not what they seem. But to reach this revelation requires courage. Our experiments cannot yet reach the Planck scale. The energies are too vast, the distances too small. The universe itself, however, may provide clues. Light that has traveled billions of years from distant gamma-ray bursts, gravitational waves rippling across the cosmos, or the faint radiation left over from the Big Bang may all carry signatures of space-time's discreteness. If space-time is grainy, then over cosmic distances, that graininess may blur signals in detectable ways. The task of the experimentalist is to search for these whispers, while the theorist constructs the possible frameworks in which they make sense. It is a long and difficult road, but not without precedent. The atomic theory of matter was once a philosophical speculation. Atoms could not be seen or touched, only inferred. For centuries, the idea remained in limbo, until evidence accumulated beyond doubt. The same may happen with the atoms of space-time. Perhaps we will never build a machine to probe directly the Planck length, but perhaps the universe itself, with its black holes and cosmic rays, will serve as our laboratory. The quest for quantum gravity is therefore not only possible, it is inevitable. Nature demands it. Our current theories cannot coexist peacefully, and history shows that such fractures always herald revolutions. As we close this chapter, the tension is clear. General relativity describes gravity as the smooth curvature of space-time. Quantum mechanics describes matter and energy as quantized, indivisible, uncertain. At the Planck scale, these two pictures collide, and neither survives intact. The quest for quantum gravity is the quest to reconcile them, to discover whether space-time itself is quantized, emergent, or something stranger still. It is the quest to move beyond the illusion of continuity into the architecture of reality itself. The path now leads to the Planck scale, the smallest ruler nature allows. There, the smoothness of space-time may dissolve, and the atoms of geometry may reveal themselves. To walk this path, we must leave behind comfort, embrace paradox, and dare to imagine that the universe is not a boundless canvas, but a mosaic, each tile no larger than the Planck length, each tick of time no longer than the Planck interval. In the next chapter, we will step across this threshold to measure nature with its smallest ruler and to confront what lies beyond the illusion. There comes a point where our instruments fail, where the smoothness of space-time can no longer be assumed, and where even imagination trembles. That point is defined not by human invention, but by nature itself. Combine 3 of the most fundamental constants of the universe, Planck's constant, the speed of light, and Newton's gravitational constant, and a scale emerges that is so extreme, it feels almost forbidden. This is the Planck scale, the frontier where all known physics collapses, and where a deeper theory must take over. It is the smallest ruler nature provides, the final tick mark before continuity may dissolve into discreteness. The Planck length is unimaginably tiny, around 10 to the power of minus 35 meters. To compare, a proton is about 10 to the power of minus 15 meters, 20 orders of magnitude larger. If a proton were magnified to the size of the observable universe, the Planck length would still be smaller than a tree. The Planck time, about 10 to the power of minus 44 seconds, is the shortest moment nature allows. Below this interval, the very concept of before and after may lose meaning. The Planck energy, about 10 to the power of 19 giga-electron volts, is far beyond anything human machines can reach. The most powerful accelerators on Earth fall short by 16 orders of magnitude. These numbers are not arbitrary. They represent the limits where quantum mechanics and general relativity clash, and where new physics must emerge. Why do these scales matter? Imagine trying to probe smaller and smaller distances by smashing particles together at higher and higher energies. At some point, the energy required becomes so large that it collapses the region into a black hole. The act of measuring space creates gravity strong enough to erase the measurement. This paradox marks the Planck length as a fundamental limit. Below it, the very idea of distance ceases to make sense. Similarly, the Planck time represents the limit of temporal resolution. To mark off a smaller slice of time would require so much energy that space-time itself would curve into collapse. These limits are not technological but fundamental. They are woven into the structure of reality. The Planck scale is therefore not merely small. It is a boundary where our familiar concepts dissolve. It is the place where smoothness shatters, where continuity falters, and where quantum gravity must reveal its face. To stand at the edge of the Planck scale is to stand at the edge of language. Our equations stretch toward infinity, then break. Our metaphors falter, for nothing in daily experience compares. Yet physics demands that we confront this frontier because the most profound questions reside here. What happened at the birth of the universe when all of space-time was compressed near this scale? What happens inside a black hole where matter collapses beyond any density we can imagine? These are Planck scale questions, and no smooth theory can answer them. One way to picture the Planck scale is as the pixel size of reality. Just as a digital image cannot display details smaller than a pixel, space-time cannot describe distances smaller than the Planck length. Just as a song sampled at a finite rate cannot contain higher frequencies, time cannot be divided more finely than the Planck interval. To think otherwise is to misunderstand the nature of information. The universe cannot encode infinite detail in a finite region. The Planck scale is the ultimate limit of information density, the point at which reality refuses to reveal more structure. Beyond it, the notion of space and time themselves may vanish, replaced by something more fundamental, something that does not resemble geometry at all. This does not mean that the Planck scale is simply a barrier. It is also a gateway. Just as atoms were discovered by pushing chemistry to its limits, and quarks by pushing nuclear physics, so too the atoms of space-time may be discovered by probing the Planck frontier. Though we cannot reach it directly with colliders, the universe itself has already explored it. The Big Bang began at Planck scales, and its imprint may still linger in the cosmic microwave background. Black holes shrink toward Planck dimensions as they evaporate, and their entropy may carry the signature of space-time quanta. Gamma-ray bursts, gravitational waves, and cosmic rays may all bear the fingerprints of Planck-scale physics. Nature has already written the story. Our task is to read it. The very existence of the Planck scale is a hint that continuity is not real. If space and time were truly continuous, there would be no smallest ruler, no final tick. Distances could always be halved, times always divided, energies always increased. But the Planck scale says otherwise. It says there is a floor beneath which the concepts of distance and time lose meaning. It whispers that continuity is a mirage, and that beneath it lies discreteness, whether in the form of loops, strings, foam, or holograms. The Planck scale is the doorway to the true architecture of reality. The very idea of the Planck scale unsettles the human mind because it imposes a flaw on reality. From childhood, we are taught that numbers can be divided forever, that between any 2 points lies another. The continuum is taken for granted, a river that can always be split into finer and finer streams. But the Planck scale tells us that this cannot be true. There is a smallest distance that can carry meaning, a shortest tick of time that can exist. Below these scales, the very language of geometry collapses, and the notion of continuity evaporates. The smooth river is revealed to be a chain of droplets, indistinguishable at first, but indivisible at last. One way to sense the profundity of this limit is to imagine building a microscope of infinite power. Each time you improve the instrument, you peer deeper, from cells to molecules to atoms to quarks. Now imagine trying to see what lies beneath a quark. You turn the knob again, magnifying further, shrinking your gaze toward the Planck length. But the attempt fails, not because the lens is weak, but because the very concept of distance dissolves. The closer you look, the more space-time curves, until the act of looking creates a black hole that hides what you sought to see. At that moment, knowledge ends. The Planck scale is not simply small, it is the veil beyond which the universe refuses to be observed. This veil does not mean that nothing exists beneath it. On the contrary, it hints at something richer, something stranger, a realm where the distinction between space, time, energy, and information may blur. Many physicists believe that the Planck scale hides the true building blocks of reality, the atoms of space-time. Just as molecules create water and quarks create protons, these quanta may create the very geometry of the cosmos. To them, the smooth fabric of relativity is like the surface of a pond, hiding the molecular dance beneath. The Planck scale is the magnification at which the molecules begin to reveal themselves. The Planck scale also raises a subtle but profound question. What does it mean for space to have a smallest unit? In our ordinary world, we can cut a stick in half, then cut the half again, continuing without end. The Planck scale says that at some point the cutting stops. The stick is no longer divided into smaller lengths of space, because the very concept of length has ended. Similarly, time may not flow as a continuous stream, but as discrete ticks, like the frames of a film. Between ticks, nothing happens, because the universe itself does not update. This idea is unsettling because it collides with our deepest intuitions. We feel time passing as a flow. We see space as infinite in its divisibility. But intuition is not physics. If reality is pixelated, then our senses are merely smoothing over the gaps. The importance of the Planck scale extends beyond metaphors. It appears wherever relativity and quantum theory must coexist. In black holes, as they shrink toward evaporation, their size approaches the Planck length. In the early universe, the entire cosmos was compressed to Planck scales. In high-energy collisions, the attempt to probe smaller distances forces energies to Planck magnitudes. Each time, the mathematics fails, collapsing into infinities or paradoxes. Each time, the Planck scale appears like a wall, reminding us that our theories are incomplete. It is not a number we invented, it is a number that nature insists upon, woven into the constants themselves. Some scientists view the Planck scale as the ultimate ultraviolet cutoff, the highest frequency or smallest wavelength reality can support. Just as sound has a limit beyond which the ear hears nothing, and light has a limit beyond which the eye sees nothing, space-time may have a limit beyond which it ceases to exist. Others imagine it as the lattice spacing of the universe, the distance between nodes of a cosmic grid. Still others see it as a horizon of emergence, the point at which space and time themselves bubble out of something deeper, like foam forming on the surface of a wave. No matter the vision, all agree that the Planck scale is the crucible where continuity dies and quantum gravity must be born. Yet the Planck scale is not only a boundary, it is a beacon. It points the way toward the next revolution in physics. Just as the atomic scale revealed chemistry and the nuclear scale revealed particle physics, so the Planck scale will reveal the true architecture of space-time. We may not yet have the instruments to probe it directly, but we have the mathematics, the paradoxes, and the clues. The Planck scale calls to us, daring us to abandon the illusion of smoothness and imagine a universe built not from continuous fabric, but from indivisible quanta of geometry. The Planck scale is often described as the smallest ruler of nature, but that phrase hides its deeper meaning. It is not simply a limit of measurement, as if our instruments were too weak. It is a limit of reality itself, a boundary built into the universe. Below the Planck length, the concept of distance may vanish. Below the Planck time, the idea of causality may falter. At the Planck energy, the very fabric of space-time may melt. The smooth surface of the cosmos, so reliable at larger scales, crumbles here into uncertainty, foam, or discrete geometry. This is why the Planck scale is not just small, but fundamental. It is the arena where the most basic features of existence dissolve into something new. The implications are staggering. If space-time is discrete, then Lorentz invariance, the sacred principle of relativity that says the laws of physics are the same in all inertial frames, may be only an approximation. At everyday scales, the approximation is perfect, but at the Planck scale, deviations may emerge. Light may travel with imperceptible jitters, gamma rays may disperse slightly over cosmic distances, or gravitational waves may shimmer with quantum noise. These effects would be vanishingly small, but across billions of years and trillions of kilometers, they might accumulate into signatures we can detect. Thus, the Planck scale is not forever hidden. It may leave faint fingerprints on the cosmos, whispers of discreteness carried by the oldest light and the most violent events in the universe. This possibility has inspired experiments that search for Planck scale effects. Telescopes watch gamma-ray bursts, looking for dispersion that could signal space-time graininess. Interferometers stretch beams of light across kilometers, hoping to detect quantum jitter in the geometry itself. Cosmic rays with unimaginable energies are studied for signs of Planck scale anomalies. So far, all results suggest that space-time is smooth. But the limits tighten. The illusion of continuity holds, but cracks may appear with sharper instruments. We are like archaeologists brushing sand from a mosaic, certain that patterns lie beneath, but uncertain of their shape. The Planck scale also reframes the deepest puzzles of cosmology. The Big Bang is often described as the beginning of space and time, but this phrase is misleading. General relativity cannot describe the first instant because it predicts a singularity of infinite density. At the Planck scale, that singularity must be resolved. Perhaps the universe bounced from a previous contraction. Perhaps it tunneled from nothing. Perhaps space and time emerged from a more fundamental order that knows nothing of geometry. Whatever the truth, the Planck scale is the key. It is the veil through which the cosmos was born, and behind which the secret of its origin lies. In black holes, the same veil appears. Relativity predicts a singularity at the center, while quantum mechanics forbids it. Somewhere before the singularity, at the Planck scale, the laws must change. Perhaps the core of a black hole is not a point, but a region where space-time quanta arrange into exotic states. Perhaps the horizon encodes all the information, pixel by pixel, in a holographic fashion. Perhaps black holes are windows into the discreteness of space itself. Each possibility is speculative, but all agree that the Planck scale is the critical arena. Thus, the Planck scale is more than a number. It is a principle, a declaration that nature refuses infinity and denies infinite divisibility. It is the recognition that the smoothness of space and time is an illusion, one that breaks at the smallest scales. The Planck scale is the horizon where new physics waits, where quantum gravity will be revealed, and where the atoms of geometry will at last be seen. It is the boundary of the known and the gateway to the unknown. And so, the journey turns. We have traced the illusion of continuity, seen its collapse in quantum mechanics, and discovered the Planck scale as the limit where reality itself demands a new description. Now we step into the attempts to answer this demand, into the theories that dare to imagine atoms of space. Some envision loops, woven into spin networks that quantize area and volume. Others imagine vibrating strings in higher dimensions, where space-time itself emerges as a song. Still others picture frothing foam, where geometry bubbles with uncertainty. Each is a radical attempt to move beyond the illusion, each a step in the quest for quantum gravity. The next chapter begins with loops, with a vision of space itself as a network, pixelated and quantized, an architecture of geometry waiting to be revealed. If the Planck scale is nature's smallest ruler, then some theory must explain what is measured by it. What lies beneath the smooth fabric of relativity? One bold answer is loop quantum gravity, a framework that dares to quantize spacetime itself. Unlike string theory, which introduces new entities such as vibrating filaments in higher dimensions, loop quantum gravity begins with the familiar and transforms it. It takes Einstein's vision of curved geometry and subjects it to the same quantization that turned waves of light into photons and vibrations of atoms into phonons. The result is a picture of space not as a continuum, but as a lattice woven from loops, where area and volume come in discrete packets, indivisible and finite. This is the first serious proposal that space-time itself is made of atoms. The origins of loop quantum gravity lie in the attempt to merge relativity and quantum mechanics without abandoning either. General relativity insists that space-time is dynamic, curved by mass and energy. Quantum mechanics insists that all dynamical systems must be quantized. Put the two together and you are compelled to quantize geometry. But how can geometry be quantized? The answer begins with rewriting Einstein's equations in a new language. Abhay Ashtekar, in the 1980s, discovered a formulation that expresses general relativity in terms of connections and loops rather than metrics and tensors. This reformulation opened the door to quantization, allowing physicists to apply the methods of quantum theory to the geometry of space. The result is extraordinary. In loop quantum gravity, space is described by networks of links and nodes called spin networks. Each link carries a quantum number. Each node connects links, and together they form a web that underlies geometry. Areas correspond to the surfaces cut by links, and volumes correspond to the nodes where links meet. These quantities are not continuous. They come in discrete values, determined by the quantum numbers of the network. Just as energy levels in an atom are quantized, so too the very fabric of space is quantized. There are smallest possible areas and smallest possible volumes. No surface can be divided without end, no volume can shrink without limit. The illusion of smoothness evaporates, replaced by a crystalline architecture of loops. To picture this, imagine zooming into a region of empty space. At ordinary scales, it appears smooth. At smaller scales, it curves gently according to relativity. But at the Planck scale, the smoothness breaks apart. What you see is a network of loops, a web of links and nodes, shimmering with quantum numbers. The geometry is no longer a fabric, but a lattice, no longer continuous, but pixelated. Each loop is like a stitch in a cosmic quilt, and together they weave the space in which we live. The atoms of space are not particles floating within geometry. They are geometry itself. This vision has profound consequences. In loop quantum gravity, singularities vanish. The Big Bang is not a point of infinite density, but a bounce, where space-time contracts to a finite minimum volume before expanding again. Black holes do not collapse to singularities, but to finite cores, where space-time loops hold up against infinite curvature. The infinities that plague relativity are tamed, not by trickery, but by discreteness. Just as quantum mechanics rescued the hydrogen atom from collapse by quantizing orbits, loop quantum gravity rescues the universe itself by quantizing geometry. The mathematics of spin networks also reveals a dynamic picture of space-time. As the network evolves, loops change, nodes split or merge, and the web transforms. This evolution is described by spin foams, higher dimensional structures that represent histories of spin networks. In this way, space-time itself becomes a process, a quantum superposition of geometries. Just as particles follow probabilistic paths, so too does geometry. The universe is not a fixed stage, but a quantum play, where the stage itself exists in many possible forms until interactions force it into definite shape. Loop quantum gravity does not solve every problem, and it remains incomplete. But it offers a radical and consistent vision that space-time is pixelated, that geometry has atoms, and that the illusion of continuity is a large-scale mirage. It does not require extra dimensions, nor exotic strings, nor unseen entities. It takes the familiar language of relativity, quantizes it, and reveals a hidden discreteness. It is a daring attempt to answer the call of the Planck scale, to show that nature's smallest ruler measures loops, not lines. Loop quantum gravity reshapes how we think about the cosmos at its most extreme. In Einstein's relativity, black holes are regions where space-time curves so strongly that not even light can escape. At the center of such a black hole lies a singularity, a point of infinite density where the laws of physics break down. In loop quantum gravity, that singularity is dissolved. The atoms of space resist infinite compression, just as the quantization of electrons resists the collapse of atoms. The loops of geometry reach a finite minimum, preventing the equations from ever producing infinities. The core of a black hole, in this picture, is not a singularity, but a region of finite density, supported by the discreteness of space-time. This resolves one of the oldest paradoxes of relativity, showing that singularities are not physical objects, but artifacts of assuming smoothness. The same reasoning applies to the origin of the universe. In classical relativity, the Big Bang is a singularity, a moment of infinite density and curvature where time begins. In loop quantum gravity, this singularity is replaced by a bounce. The universe contracts until it reaches a minimum volume determined by the Planck scale, then rebounds and begins expanding. This cosmic bounce means that time did not begin at the Big Bang. Instead, there was a universe before ours, perhaps many before, each collapsing and rebounding in an eternal cycle. The atoms of space give the universe resilience, preventing it from dissolving into nothingness. Continuity fails, but discreteness saves reality itself. The consequences ripple outward. If space-time is made of atoms, then area and volume are not smooth but quantized. The surface of a black hole has an entropy proportional to its area, measured in Planck units. Loop quantum gravity provides a microscopic explanation for this, counting the possible configurations of loops that form the horizon. Each configuration is like a pixel on a screen, carrying one bit of information. The entropy of the black hole is then nothing more than the number of ways these pixels can be arranged. In this way, loop quantum gravity supports the holographic principle, suggesting that the information content of a region of space is stored on its boundary. The pixels of space are the ultimate bits of information. But loop quantum gravity does not stop with black holes and cosmology. It also reimagines the flow of time. In relativity, time is a dimension, woven together with space into a four-dimensional fabric. In loop quantum gravity, time may be emergent, arising from the evolution of spin networks. The network changes, loops expand or shrink, nodes merge or split, and from this evolution, we perceive time. In this view, time is not fundamental, but a manifestation of change, a measure of how the atoms of space rearrange themselves. If so, then the illusion of continuity extends not only to space, but also to time. The ticking of a clock may be nothing more than the unfolding of loops. This vision is radical, yet it preserves the beauty of relativity. Space-time is still dynamic, still curved by mass and energy, still the stage upon which galaxies form and stars collapse. But beneath the smooth curvature lies a network. Beneath the fabric lies a weave. Relativity describes the large scale, where loops are too fine to notice, just as fluid dynamics describes water without mentioning molecules. At smaller scales, the weave of loops becomes apparent. and the discreteness of geometry transforms our understanding. Relativity is not wrong. It is incomplete, an approximation valid where the atoms of space blur into smoothness. There is something deeply satisfying in this. Again and again in physics, infinities signal incompleteness, and quantization resolves them. The collapse of the atom was prevented by quantized orbits. The ultraviolet catastrophe of blackbody radiation was cured by quantized photons. The infinities of black holes and the Big Bang may be cured by quantized geometry. Loop quantum gravity fits this pattern, extending the principle of quantization to the very stage of existence. It tells us that smoothness is a mirage and discreteness is the truth. Yet challenges remain. Loop quantum gravity is mathematically complex, and though it resolves singularities and explains black hole entropy, it has not yet made unique predictions that can be tested. The framework is elegant, but without experimental confirmation, it remains a hypothesis. Still, it stands as one of the boldest attempts to reconcile relativity and quantum mechanics, not by compromise, but by revolution. It declares that space itself is made of atoms, that the Planck scale is their size, and that continuity is an illusion. The picture drawn by loop quantum gravity is daring, yet it remains grounded in the logic of physics. It does not invent exotic ingredients, but instead applies the same principle of quantization that has succeeded so often before. Light, energy, matter, and motion have all yielded to quantization. Why not geometry itself? By following this logic, loop quantum gravity reveals a world where space is woven from loops, where volumes and areas are discrete, and where time itself may be an emergent rhythm of changing networks. It is a vision that transforms the cosmos from a smooth expanse into a crystalline structure, an architecture of atoms of space. Yet this vision is not without challenges. The mathematics of spin networks and spin foams is complex, and many details remain unsettled. While the theory explains black hole entropy and resolves singularities, it struggles to reproduce the familiar particles and forces that quantum field theory describes so well. It is a theory of geometry more than a theory of matter, a framework for the stage rather than the actors. Some physicists argue that it may need to be combined with other ideas before it can describe the full richness of reality. Still, the core insight, that space is quantized, stands as a profound step toward quantum gravity. One of the most cinematic consequences of loop quantum gravity is its portrayal of the early universe. Instead of emerging from a singularity, the cosmos bounces. A previous universe contracts until it reaches Planck scale density, then rebounds into expansion. Our Big Bang becomes not a beginning, but a transition, a bridge between aeons. The atoms of space prevent collapse into nothingness, ensuring that reality continues through cycles of contraction and rebirth. This image is breathtaking. It suggests that the universe is eternal, that time stretches not from a beginning to an end, but through endless loops, each carried by the loops of geometry themselves. The cosmos becomes a phoenix, burning and rising, collapsing and rebounding, forever renewed. For black holes, the implications are equally striking. If singularities do not exist, then information may not be lost. The entropy of a black hole, explained by the number of possible loop configurations on its horizon, implies that the information content of matter falling in is preserved in the geometry. Hawking's paradox, which pitted relativity against quantum mechanics, may be resolved by discreteness. If black holes are not holes to nowhere but finite regions held up by atoms of space, then their evaporation need not destroy information. The holographic surface encodes it, bit by bit, pixel by pixel. In this way, loop quantum gravity not only preserves physics, but preserves meaning itself, rescuing information from annihilation. To accept this vision is to abandon the illusion of smoothness. Just as the discovery of atoms shattered the ancient belief in continuous matter, loop quantum gravity shatters the belief in continuous space. The difference is scale. Atoms of matter are unimaginably small, but atoms of space are smaller still, hiding beneath 20 orders of magnitude beyond our reach. Yet invisibility is not non-existence. The mathematics, the paradoxes, and the principles all point to discreteness. The loops are there, even if our eyes and instruments cannot yet see them. As this chapter closes, the contrast sharpens. Loop quantum gravity builds space-time from loops, quantizing geometry itself. But it is not the only vision. Another path, string theory, begins not with loops of geometry, but with vibrating strings of energy. Where loop quantum gravity sees atoms of space, string theory sees space as emergent from a deeper harmony of vibrations. Where one sees networks of loops, the other sees holograms projected from higher dimensions. Both reject smoothness, but they do so in radically different ways. To understand the full spectrum of possibilities, we must now turn to the second great contender in the quest for quantum gravity, a theory that dares to suggest that space-time itself is not fundamental, but born from the music of strings. If loop quantum gravity imagines space-time as woven from loops, string theory imagines reality itself as composed of vibrating filaments of energy. Where loop quantum gravity quantizes geometry directly, string theory shifts the question. It does not ask how to quantize space-time. It asks whether space-time is even fundamental at all. Perhaps space and time are emergent, arising from something deeper, something that vibrates like the strings of a cosmic instrument. In this view, the true building blocks of the universe are not points or loops, but tiny strings, each vibrating with its own frequency, each producing the particles and forces we observe. From the music of these strings, space-time itself may emerge as harmony. The origins of string theory were unexpected. In the 1960s, physicists sought to explain the strong nuclear force, the binding that holds protons and neutrons together. A peculiar mathematical formula called the Veneziano amplitude seemed to describe the scattering of strongly interacting particles with remarkable accuracy. At first, no one understood why. Then came the realization that the amplitude could be explained if the particles were not points, but strings, tiny one-dimensional objects whose vibrations produce the observed interactions. Though quantum chromodynamics would later replace this model for the strong force, the idea of strings refused to fade. Physicists noticed that strings naturally included a massless spin-2 particle, exactly what a quantum graviton should be. The theory that had begun as an attempt to explain nuclear physics turned out to contain gravity itself. This was a revelation. For decades, attempts to quantize gravity had failed, producing uncontrollable infinities. String theory offered a new way. By replacing point particles with strings, the interactions became smoother, the infinities tamed. The theory seemed to resolve the clash between relativity and quantum mechanics. But it demanded a price. Strings cannot vibrate consistently in 3 spatial dimensions and 1 time dimension. They require more. The mathematics insists on 9 or 10 spatial dimensions, plus time. The extra dimensions are hidden, curled into shapes too small to see, but they are essential to the harmony of strings. Our universe of 3 dimensions may be a projection, a visible slice of a higher dimensional symphony. This idea is radical, but it carries profound explanatory power. The different vibrations of strings correspond to different particles. One vibration produces an electron, another a quark, another a graviton. All matter and forces become different notes of the same instrument. Instead of treating particles as separate entities, string theory unifies them as harmonics of strings. Gravity itself is no longer an anomaly, but a natural consequence. The smooth fabric of space-time is not fundamental, but emerges from the interplay of vibrations. In this way, string theory fulfills the dream of unification, not by patching equations together, but by revealing a common foundation beneath them all. To picture this, imagine a violin string vibrating. Its fundamental tone is joined by harmonics, each producing a distinct note. Now shrink the string to the Planck scale and imagine it vibrating in many dimensions. Each vibration is a particle, each note a force of nature, and together they form the symphony of the universe. The particles we observe are not fundamental grains of matter, but echoes of deeper vibrations. Space and time themselves may be the resonant medium that emerges when countless strings interact. Just as the surface of water emerges from the motion of molecules, space-time emerges from the music of strings. The most breathtaking aspect of this vision is the holographic principle. According to this idea, the information contained within a region of space can be described entirely by data encoded on its boundary, like a hologram projecting 3 dimensions from 2. In the 1990s, this principle was given precise form in the discovery known as ADS-CFT duality. It states that a string theory defined in a higher dimensional curved space can be exactly equivalent to a quantum field theory without gravity on its boundary. This duality suggests that space-time itself is not fundamental but emergent, a projection of quantum interactions that live elsewhere. Our universe may be a hologram, not an illusion, but a precise encoding, where the smoothness of space-time is a shadow of deeper dynamics. String theory, then, is not just a theory of strings. It is a theory in which space-time itself arises from deeper structures. It is a challenge to everything we take for granted, a call to see reality not as a continuous stage, but as an emergent harmony. It rejects the illusion of continuity by denying the fundamentality of space and time. Where loop quantum gravity replaces smoothness with loops, string theory replaces smoothness with music. The mathematics of string theory opens windows into realms of reality that stretch imagination to its breaking point. The extra dimensions required by the theory are not decorations, but essential to its consistency. Without them, the strings cannot vibrate in ways that produce the rich spectrum of particles we observe. These hidden dimensions are thought to be compactified, curled into intricate shapes far smaller than the Planck length, invisible to any current experiment. Their geometry determines the notes the strings can play, much as the shape of a violin determines its resonance. In this way, the architecture of unseen dimensions dictates the laws of physics in our visible universe. The masses of particles, the strengths of forces, even the existence of families of quarks and leptons may all trace back to the geometry of curled dimensions. These hidden dimensions are not merely mathematical curiosities. They may explain mysteries that haunt cosmology. Dark energy, the force driving the accelerated expansion of the universe, could arise from the vacuum energy of strings vibrating in compact dimensions. Dark matter, the unseen mass that outweighs visible matter by 5 to 1, could be composed of stringy excitations or extended objects called brains. The richness of possibilities is staggering, yet the mathematics is relentless. It does not allow a single unique universe, but an enormous landscape of possible solutions, each corresponding to a different way of curling the extra dimensions. Some estimate that this landscape may contain as many as 10 to the power of 500 possible universes. Our cosmos may be only one valley among countless others, chosen not by inevitability, but by chance or necessity. This idea leads to the possibility of a multiverse, a vast ensemble of universes with different laws of physics, each born from a different configuration of strings and dimensions. In most, stars and galaxies might never form. In others, matter might be unstable. In ours, the balance is just right for complexity, for chemistry, for life. Some see this as a weakness, a retreat into speculation. Others see it as a natural extension of string theory, a recognition that the laws we observe are not absolute, but contingent, one pattern among many. Whether true or not, the concept shifts our place in reality. We may live not in the only universe, but in one universe among a cosmic sea, its laws carved by the vibrations of strings in hidden dimensions. the holographic principle deepens this vision. In ADS-CFT duality, a string theory living in a curved higher dimensional space is exactly equivalent to a quantum field theory without gravity on its boundary. This means that space-time itself, with its gravity and geometry, can be reconstructed from interactions that do not contain space-time at all. The smoothness of geometry is not fundamental, but emerges from entanglement, the deep quantum connection between states. Imagine weaving a tapestry where each thread is a strand of entanglement. The more threads you weave, the stronger the tapestry. In the same way, the more entanglement in the boundary theory, the smoother the emergent space-time. This idea suggests that geometry is nothing but the fabric of entanglement. Space itself is quantum information made visible. If this is true, then the illusion of continuity is not only an approximation, but a mirage of emergence. Space and time may not exist independently of matter and information. They may be born from the entanglement of quantum states. In this view, the true reality is not geometric, but informational. The pixels of the universe are not loops of space, but bits of entanglement, woven together to project the space-time we experience. The smoothness of the cosmos is then a property of information, not of geometry. The stage is no longer even a stage. It is a projection of relationships, a hologram of quantum music. These ideas are breathtaking, but they remain distant from direct experimental confirmation. String theory makes predictions only at energies far beyond our reach. The extra dimensions are hidden too small to probe. The multiverse, if real, may be forever beyond observation. Yet the mathematics continues to seduce. It unifies gravity with quantum mechanics, tames infinities, and offers a vision where space-time itself is emergent. Many physicists see in string theory the most promising path toward quantum gravity. Others see it as a beautiful mirage, a mathematical cathedral unanchored from empirical ground. Whatever its fate, string theory forces us to confront the possibility that space-time is not fundamental. If the loops of loop quantum gravity are atoms of space, the strings of string theory are music from which space itself emerges. Both reject smoothness, both deny continuity, both ask us to abandon the stage and see reality as a deeper play. String theory stands as one of the boldest reimaginings of reality ever attempted. It dares to suggest that what we see as the fundamental ingredients of nature are not truly fundamental. Electrons, quarks, photons, gravitons, all may be nothing more than echoes of vibrating strings. Their masses, their charges, their interactions, all determined by the patterns of vibration in a space richer than the one we perceive. The geometry of hidden dimensions becomes the score, and the universe becomes the music. This is not merely a new theory of particles, it is a new ontology, a new way of understanding existence. The illusion of smoothness dissolves not into loops of geometry, but into harmonies of vibration. Yet the ambition of string theory is also its burden. The mathematics is vast and intricate, and the landscape of possible solutions may be so immense that uniqueness is lost. The theory explains much, but predicts little that can be tested with current experiments. Its strings vibrate at energies far beyond any collider we can build. Its extra dimensions are curled so tightly that they evade all detection. Its multiverse may be forever inaccessible. For critics, this is disheartening. A theory too beautiful to abandon, but too distant to confirm. For supporters, it is a challenge, a puzzle whose resolution requires new imagination, new experiments, new ways of seeing the cosmos. In either case, string theory forces us to face the possibility that space and time are not bedrock, but emergent, not givens, but consequences. The holographic principle is perhaps the most astonishing gift of string theory. If it is true that the information within a region of space is encoded on its boundary, then our intuitive notion of volume is an illusion. The true degrees of freedom reside not in the bulk, but on the surface. This changes everything. Black holes, once paradoxical, become natural. Their entropy is simply the number of boundary bits. Space-time itself, once assumed continuous, becomes an emergent encoding. Entanglement is the thread, and geometry is the cloth it weaves. Continuity is not real, it is a mirage arising from information. To live in such a universe is to live in a hologram, not a false hologram, but a real one. A precise encoding where reality itself is projection. And yet, despite its abstractions, string theory circles back to the same question that haunts loop quantum gravity. The same question raised by the Planck scale. The same question that lurked behind Zeno's paradoxes and Newton's calculus. Is space continuous or is it discrete? String theory's answer is subtle. It does not say space is made of loops or grains. It says space may not exist at all in the way we think. It may be a derived property, an emergent pattern, a harmony arising from the deeper language of strings and entanglement. Continuity is then not an illusion hiding discreteness, but an illusion hiding emergence. Space and time are not fundamental, they are born. This reimagining is unsettling, yet it opens doors. If space is emergent, then causality itself may be emergent. If time is emergent, then determinism may be emergent. The foundations of physics become shadows of deeper principles. The search for quantum gravity thus becomes not only a search for discreteness, but for emergence, not only for atoms of space, but for the music of existence. String theory does not prove that space-time is emergent, but it shows that such a vision is possible, consistent, and mathematically compelling. It offers a cosmos where smoothness is not destroyed, but transcended, where continuity is not denied, but explained. As this chapter closes, the two visions stand before us. Loop quantum gravity says space-time is made of atoms, quantized like everything else. String theory says space-time is not fundamental, but emergent from the vibrations of strings and the entanglement of quantum fields. One builds reality from loops, the other from music. One quantizes geometry, the other replaces geometry with harmony. Both point beyond continuity. Both tell us that the seamless stage of relativity is not the final truth. To step further, we must now consider another vision, one born not from loops or strings, but from the restless imagination of John Wheeler, who pictured space-time itself as a foam, bubbling with uncertainty at the Planck scale. When Einstein described space-time as a smooth fabric, it seemed natural to imagine it as serene, like a calm ocean stretching infinitely in every direction. But John Wheeler, one of the great architects of modern physics, dared to see something far stranger. In the 1950s, he proposed that space-time, when examined at the Planck scale, is not smooth at all, but seething with activity. Just as the quantum world forbids particles from sitting still, so too it forbids space-time from remaining calm. At the smallest scales, geometry itself must fluctuate wildly. Distances and durations blur, horizons tremble, and space foams with uncertainty. This vision is called quantum foam, a churning sea of space-time at its most fundamental. The idea arises naturally from quantum mechanics. According to the uncertainty principle, energy and time cannot both be determined with arbitrary precision. For very short durations, large fluctuations of energy are possible. These fluctuations manifest as virtual particles appearing and disappearing, lending the quantum vacuum its restless character. If energy fluctuates, and if energy bends space-time, then space-time itself must fluctuate. The shorter the scale, the wilder the fluctuations. At the Planck length, the fluctuations are so violent that the smoothness of geometry dissolves into foam. Space-time becomes a frothing chaos of bubbles, wormholes, and flickering geometries, constantly appearing and vanishing in Planck intervals of time. It is difficult to picture such a world. At our scale, space-time is so calm that we can treat it as a rigid stage. Even black holes curve it smoothly, and gravitational waves ripple gently through it. But zoom in to the Planck scale, and the stage dissolves. Imagine an ocean seen from a satellite, smooth and unbroken, Now dive into the water and look closely. You see foam, bubbles, and turbulence. Wheeler's quantum foam is like that. At large scales, space-time is smooth. At small scales, it foams with fluctuations. Continuity is an illusion born of distance, hiding the restless sea beneath. This foam may contain exotic features. Tiny wormholes may flicker in and out of existence, microscopic tunnels connecting distant regions of space before collapsing back into nothing. Quantum fluctuations may briefly create tiny black holes, evaporating in flashes of Hawking radiation. The geometry itself may fluctuate so much that the concept of distance loses meaning. In Wheeler's vision, the Planck scale is not simply a boundary, but a storm. The atoms of space, if they exist, are tossed in froth. Time itself may jitter, refusing to tick steadily. The foam is a universe within the universe, invisible to us, but fundamental to everything. Quantum foam also provides a way to think about the limits of knowledge. If space-time is foamy, then no measurement can pin down distances or times below the Planck scale. Just as quantum mechanics sets a limit on how precisely we can know position and momentum, quantum foam sets a limit on how precisely we can know geometry. Reality itself becomes uncertain. The length of a path is not fixed but fluctuates. The duration of an event is not absolute but blurred by foam. Continuity is not merely approximated but denied. The universe is not built on a smooth foundation but on a restless sea of quantum geometry. This vision may seem fantastical, but it carries testable consequences. If space-time is foamy, then light traveling across cosmic distances may be affected. Photons from distant gamma-ray bursts may accumulate tiny delays, dispersing their arrival times. Gravitational waves rippling across the universe may be distorted by jitter in geometry. Even the interference patterns of lasers on Earth may carry the signature of foam. Detecting such effects is immensely difficult, but not impossible. The foam, if real, is not hidden forever. It leaves faint traces in the cosmos, whispers of turbulence beneath the smoothness we see. Wheeler's idea of quantum foam also reshaped philosophy. If space-time is frothing, then geometry is not primary. It is emergent from fluctuations, an average of chaos. The illusion of smoothness is not even an approximation, but a statistical blur, like the calm surface of a sea that hides waves and bubbles beneath. This forces us to rethink what space and time are. They may not be containers at all, but consequences of deeper quantum processes. Continuity is then not a property of the universe, but a mirage of scale. Zoom out, and the foam looks smooth. Zoom in, and smoothness dissolves. Quantum foam is more than a metaphor. It is a way of saying that space-time, when pushed to its limits, cannot be frozen into a fixed form. Just as particles cannot sit still because of quantum uncertainty, geometry cannot remain flat or curved in a stable way at the Planck scale. It must fluctuate, jittering from one configuration to another, like a candle flame flickering in the wind. These fluctuations are not minor ripples, but profound distortions. They twist distances, scramble directions, and blur the very notion of locality. A point in space-time may not remain a point. It may smear into a cloud, its coordinates no longer sharply defined. In this world, the very language of geometry fails. Straight lines, smooth surfaces, continuous paths, all dissolve into uncertainty. One consequence of such fluctuations is the possible appearance of microscopic wormholes. These are not the majestic tunnels of science fiction, large enough for spaceships, but tiny throats opening and closing in Planck timescales. They would be quantum shortcuts, flickering bridges between regions of space that vanish before anything can cross. Some physicists speculate that such wormholes could play a role in the entanglement of particles, perhaps even serving as the geometric fabric of quantum connections. In this vision, entanglement and wormholes are two sides of the same coin. The foam is not just chaotic, but structured. weaving the threads of quantum relationships into the geometry of space-time itself. The foam may also produce tiny black holes, born from fluctuations of energy that briefly exceed the threshold of collapse. These miniature black holes would evaporate almost instantly through Hawking radiation, vanishing back into the foam. Their existence would further emphasize the instability of geometry at the smallest scales. In the foam, horizons and singularities are not permanent features, but transient flickers. Reality becomes a restless dance of appearances and disappearances, a storm of birth and death at the Planck frontier. The challenge is to connect this vision to observation. If the foam is real, its influence should accumulate over vast distances. Consider a photon of light leaving a galaxy billions of light years away. Each Planck length it travels, space-time jitters slightly. Over short distances, the jitter averages out, but over billions of light years, the cumulative effect may become noticeable. The photon's path may deviate, its arrival time may blur, or its energy may shift. Astronomers have searched for such effects in gamma-ray bursts, those cosmic explosions that send photons racing across the universe. So far, the results suggest that space-time is remarkably smooth, placing strict limits on the scale of foaminess. But the search continues, and every new burst is a test of Wheeler's vision. On Earth, physicists have sought foam in the interference of lasers. In interferometers, light is split into two beams that travel different paths before recombining. If space-time jitters at the Planck scale, then the paths may fluctuate, producing noise in the interference pattern. Experiments such as the holometer at Fermilab have searched for this holographic noise, listening for the hiss of space-time itself. No signal has yet been found, but the absence of noise constrains the possible forms of foam. Even silence teaches us something. It tells us how smooth space-time must be, and how subtle its fluctuations, if they exist. The idea of quantum foam also resonates with the holographic principle. If information within a region is encoded on its boundary, then the foam inside may be a projection of boundary fluctuations. Geometry and information intertwine, with foam serving as the microscopic manifestation of entanglement. In this view, the foam is not random chaos, but the quantum texture of reality, encoding the bits of the universe in bubbles and fluctuations. Continuity is the illusion created when we average over this froth, much as a smooth field of grass looks continuous from afar, but reveals blades and gaps up close. Wheeler himself imagined the foam as a playground of possibilities, a realm where space-time bubbles, splits, and reconnects endlessly. He believed that the foam was the foundation of everything, the source from which geometry, matter, and even the laws of physics might emerge. It was not a decorative feature, but the essence of reality. If true, then to understand the foam is to understand the origin of the universe. The calm fabric of Einstein is only the surface. Beneath it, Wheeler's storm rages on, hidden from our senses but shaping everything we see. Quantum foam is an unsettling vision because it undermines our most basic assumptions. We imagine space as a container and time as a flow, but in the foam neither container nor flow exists in a stable way. The geometry itself flickers, the flow itself jitters, continuity dissolves into turbulence. To live in such a universe is to live on the calm surface of a storm, unaware of the chaos beneath. And yet, it is precisely this storm that may hold the key to the deepest mysteries. If the foam exists, then it is here that black holes lose their singularities, here that the Big Bang avoids infinities, here that information is preserved rather than destroyed. The foam is not noise, but the structure of reality itself. The philosophical implications are profound. If space and time are foamy, then they are not fundamental. They are emergent, statistical averages of quantum chaos. Geometry is no longer the foundation of physics, but a consequence. This changes the very notion of what physics seeks to explain. No longer is the goal to describe space and time as given entities. The goal becomes to explain how they emerge from fluctuations, how continuity arises from foam. In this vision, space-time is not a stage, but a performance, not a backdrop, but an effect. The calm fabric of Einstein is a mirage painted by averages, while Wheeler's foam is the reality beneath. The question then becomes, can we ever confirm this vision? The foam exists at the Planck scale, far beyond direct reach. But like distant mountains glimpsed through haze, it may cast shadows that we can detect. Photons traveling billions of years may accumulate distortions. Gravitational waves sweeping across the cosmos may pick up jitters. Experiments on Earth may hear faint whispers of noise. Each search is a probe into the foam, a hand reaching into turbulence. Each result, whether signal or silence, narrows the possibilities. The absence of foam is itself information, forcing theories to refine, adapt, or collapse. Even if the foam remains hidden, its logic is irresistible. Quantum mechanics demands fluctuations. General relativity demands that energy curves space-time. Combine them, and foam is inevitable. It is the unavoidable marriage of uncertainty and geometry. Whether we can detect it or not, the foam is a natural consequence of the principles we already accept. To deny it is to deny the union of quantum mechanics and relativity. To embrace it is to accept that continuity is an illusion, and that beneath the smoothness lies a sea of bubbling chaos. Wheeler once said that space-time tells matter how to move, and matter tells space-time how to curve. The foam adds a deeper twist. At the Planck scale, space-time cannot tell matter anything with certainty, because it is itself uncertain. Matter cannot curve space-time smoothly, because space-time is not smooth. The dialogue between matter and geometry becomes a conversation in whispers, full of hesitations and stutters. Out of this imperfect dialogue emerges the smooth world we see. The foam is the foundation of the cosmos, yet it hides beneath layers of calm. It is the storm beneath the surface, the flicker beneath the glow, the turbulence beneath the fabric. As this chapter closes, Wheeler's vision leaves us with a challenge. If the universe is built from foam, then our task is to detect it, to measure its ripples, to confirm its presence. The next step is to ask whether such foaminess can be revealed by experiment, whether photons, gravitational waves, or lasers can expose the pixelation of space. For so far, space-time looks smooth, but appearances can deceive and illusions can endure until instruments are sharp enough to pierce them. The search for experimental clues begins. For centuries, the deepest revolutions in physics began not with speculation, but with observation. Atoms were once philosophical ideas, until the Brownian motion of dust gave them away. Quantum mechanics was a mathematical oddity, until experiments revealed the discreteness of energy. Even relativity, so abstract in its conception, was confirmed by the bending of starlight and the ticking of atomic clocks. Theories rise and fall, but experiments hold the final word. If space-time is pixelated, then the ultimate test lies not in equations, but in observation. The challenge is immense. The Planck scale is so far beyond human reach that no collider can probe it directly. Yet nature offers us tools. The universe is vast, and in its depths lie experiments already running, waiting for us to read their results. Photons traveling across billions of light years, gravitational waves rippling through the cosmos, and delicate instruments on Earth all offer glimpses into the possible discreteness of space-time. One of the most promising sources of clues is the light from gamma-ray bursts. These explosions are among the most violent events in the universe, releasing in a few seconds more energy than the sun will emit in its entire lifetime. Their photons travel for billions of years before reaching our telescopes, crossing cosmic expanses where even the tiniest distortions could accumulate. If space-time is foamy, then photons of different energies might not travel at exactly the same speed. Higher energy photons could be delayed or advanced by tiny amounts as they weave through the foam. Over short distances, the difference would be undetectable, but over billions of light years, it might add up to milliseconds, enough for us to measure. Observing such delays would be a direct signature of pixelated space. Astronomers have searched carefully for these effects. Satellites such as the Fermi Gamma Ray Space Telescope have measured the arrival times of photons from distant bursts with extraordinary precision. So far, no delays consistent with foam have been found. The photons, even those of vastly different energies, arrive together to within fractions of a second. This tells us that if space-time is foamy, its effects are subtler than the simplest models predict. The universe appears smooth, at least up to the scales we can test. But silence is not defeat. It is guidance, narrowing the possibilities, telling us that if space-time is pixelated, it must be so in a way that preserves the apparent constancy of light across cosmic distances. Gravitational waves offer another window into the structure of space-time. These ripples in geometry, first predicted by Einstein and detected a century later by LIGO, travel across the cosmos, carrying information about cataclysmic events such as colliding black holes. If space-time is discrete, then these waves may not travel perfectly smoothly. They may scatter off the foam, jitter slightly, or accumulate noise. The detectors, which measure changes smaller than a fraction of a proton's width, are sensitive enough to hear whispers of such distortions. With each detection, physicists listen not only to the story of black holes, but to the structure of space-time itself. So far, the waves arrive pristine, with no detectable noise beyond what relativity predicts. But as detectors improve, probing lower frequencies and longer baselines, they may yet reveal hints of graininess in the geometry they ride upon. On Earth, experiments push the search in different ways. At Fermilab, the holometer was designed to test whether space-time itself has a holographic noise, a jitter arising from its pixelated structure. Using powerful lasers split into beams traveling along perpendicular paths, the holometer searched for correlated fluctuations that would signal the fundamental limits of space-time resolution. If space is holographic, then its information content is finite, and the jitter of photons in the interferometer might betray this limit. After years of operation, the holometer reported no such noise, placing strong bounds on the possible pixelation of space. Once again, smoothness prevailed. But once again, the absence of evidence sharpened the boundaries of possibility, telling us that if space-time is holographic, its scale lies deeper than we can yet reach. The message from these experiments is clear. The universe, as far as we can see, is astonishingly smooth. Light from explosions billions of years away, ripples from black holes colliding in darkness, and the whispers of lasers on Earth all affirm continuity. Yet this smoothness is itself a clue. It tells us that if discreteness exists, it is hidden well, encoded subtly, revealed only at scales beyond our current reach. It tells us that the illusion of continuity is powerful, but not unassailable. The search for experimental clues continues, because history has shown that beneath smoothness often lies discreteness, waiting for instruments sharp enough to reveal it. The search for signs of discreteness does not end with photons and gravitational waves. Cosmic rays, those high-energy particles that strike Earth's atmosphere from distant galaxies, also serve as probes of spacetime's texture. Some cosmic rays carry energies far beyond what any particle accelerator on Earth can achieve. They are nature's own experiments at scales close to the Planck frontier. If spacetime were foamy, these particles might lose energy in unexpected ways or scatter off the quantum graininess of geometry. Yet when we observe them, they travel extraordinary distances with their energies intact, striking detectors with no sign of scattering. Their very survival across cosmic expanses sets strict limits on how much jitter spacetime can contain. Once again, the message seems to be that continuity holds, or that pixelation, if real, hides its presence with astonishing subtlety. Neutrinos, those ghost-like particles that stream through matter with hardly any interaction, provide another test. They are born in nuclear reactions, in supernova explosions, and perhaps in gamma-ray bursts themselves. Their weak interactions allow them to travel across the universe unimpeded, carrying pristine information about the places they came from. If space-time were grainy, neutrinos of different energies might arrive at different times, scattered by the foam. Observatories such as IceCube, buried deep in the Antarctic ice, watch for these particles, measuring their energies and arrival times with exquisite precision. So far, neutrinos too show no sign of dispersion. They arrive when they should, their paths seemingly undisturbed by any hidden grain. The foam, if it exists, conceals itself well. Closer to home, physicists continue to refine instruments that push the limits of sensitivity. Interferometers like those at LIGO and Virgo, originally designed to detect gravitational waves, may also be tuned to search for the jitter of space-time itself. If space is quantized, then light beams traveling along different arms of the interferometer might accumulate uncorrelated noise, a faint but distinctive hiss betraying the discreteness of geometry. Thus far, no such noise has been found. But future generations of detectors, larger and more precise, may yet reveal what lies beneath the apparent smoothness. The quest is ongoing, each null result narrowing the realm in which pixelation can hide. The absence of evidence does not imply the absence of discreteness. History reminds us of this. Atoms were once invisible, their existence doubted for centuries. It was only when experiments reached sufficient precision that their presence became undeniable. Quarks too remained hidden until colliders revealed their fingerprints. The same may be true of the atoms of space. They may be so deeply concealed that only the most delicate experiments or the most extreme cosmic events can reveal them. Patience is required. The universe does not give up its secrets easily. Yet it does give them up, eventually, to instruments sharpened and questions refined. One of the most intriguing possibilities is that the holographic principle itself might leave measurable traces. If space-time encodes information on surfaces rather than volumes, then there may be a fundamental limit to how precisely positions can be defined. This limit would manifest as holographic noise, a jitter in the geometry itself. Experiments like the holometer have searched for such noise without success, but future devices may reach deeper. The holographic vision suggests that the smoothness we see is an illusion born of averaging over limited information. If so, then the limits of information must eventually reveal themselves. Detecting such limits would be nothing less than detecting the pixels of space. The pursuit of experimental evidence for pixelation is therefore not futile, but essential. Each test, whether it finds foam or not, refines our understanding. Each null result is a step toward the truth, telling us how subtle, how hidden, or how emergent the atoms of space-time must be. The illusion of continuity has survived scrutiny before, but illusions always have limits. The question is not whether space-time will yield its secrets, but when, and with what instruments. The experiments searching for the discreteness of space-time tell a paradoxical story. On the one hand, they reveal no evidence of foam, no jitter in the geometry, no dispersion of light across billions of light years. The cosmos appears astonishingly smooth, as if space-time were truly continuous. On the other hand, theory insists that smoothness must be an illusion. Quantum mechanics demands fluctuations, relativity demands curvature, and at the Planck scale, the two collide in ways that cannot be reconciled by continuity. The absence of evidence is not the absence of discreteness. It is the whisper of a secret held more tightly than we imagined. This tension fuels the search. Each gamma ray burst observed, each gravitational wave detected, each cosmic ray measured is another chance to catch space-time in a lie. So far, space-time has not confessed. The photons arrive together. The waves ripple smoothly. The cosmic rays carry their energy across unimaginable distances. Even the holometer, straining to detect holographic noise, reported silence. Yet this silence itself is a discovery. It tells us that space-time, if pixelated, is more subtle than our simplest models predict. It tells us that continuity, though an illusion, is an illusion of extraordinary power, one that resists detection across scales vast and small. But physics thrives on such resistance. The stubbornness of nature is what drives theory forward. When atoms were doubted, it was because their discreteness left no obvious trace at human scales. When quantum mechanics first appeared, it was because energy quantization seemed invisible until instruments became sensitive enough to detect it. The same pattern may hold for space-time. Its pixelation may be hidden beneath layers of smoothness, awaiting only the right lens to reveal it. The cosmos is vast, and it carries signals older than galaxies, brighter than suns, and more violent than supernovae. These signals may yet betray the discreteness of geometry. The search is far from over. Indeed, there is reason to hope. Technology advances relentlessly. New detectors of gravitational waves, spanning continents and perhaps even orbiting in space, will probe space-time with greater precision. Telescopes with higher resolution will watch gamma-ray bursts in unprecedented detail. Cosmic ray observatories will measure particles of unimaginable energy, and interferometers, tuned with ever greater sensitivity, may listen to the hiss of space-time itself. Each step sharpens our ears and eyes. Each step draws us closer to the Planck frontier. If space-time is pixelated, the day will come when its pixels are revealed. Yet there is another path to discovery, one that does not rely on direct detection of foam or noise, but on the paradoxes of black holes. Black holes are natural laboratories of quantum gravity, places where relativity and quantum mechanics collide head-on. Their entropy, their radiation, and their information paradox all point toward discreteness. They suggest that space-time cannot be continuous, that its true structure is made of finite bits, pixels of area on horizons, quanta of geometry at cores. Where experiments on Earth struggle, black holes may already hold the answers. To understand them is to understand the pixelation of space. As this chapter closes, the search for experimental clues leaves us with both frustration and promise. Space-time appears smooth, yet we know it cannot be. Instruments reveal nothing, yet each null result refines the map of possibility. The universe guards its secrets well, but it cannot guard them forever. The smoothness of space-time is an illusion, and like all illusions, it will one day be pierced. The next step in our journey is to confront the black holes themselves, those cosmic furnaces where information, entropy, and geometry intertwine. It is there that the strongest evidence for pixelation may already reside, encoded in the very horizons of the universe's darkest objects. Black holes are among the strangest predictions of general relativity and among the most terrifyingly real objects in the cosmos. They are born when massive stars collapse under their own gravity, when nothing can resist the pull of space-time bent beyond return. In Einstein's theory, a black hole is defined by its event horizon, the surface beyond which no signal, no particle, not even light, can escape. From the outside, the horizon is a perfect veil. Whatever falls in is hidden forever. The black hole becomes an object defined not by its contents, but by its boundary. To an observer, it is described by only a few numbers: its mass, its charge, and its spin. The richness of matter and structure that collapse to form it is erased. This is the black hole's first paradox. How can complexity vanish so completely into simplicity? In the early 1970s, Jacob Bekenstein asked a daring question. If black holes hide information, do they also carry entropy? Entropy is the measure of disorder, the number of microscopic states that correspond to a macroscopic system. A hot gas has high entropy because its atoms can be arranged in countless ways while still producing the same pressure and temperature. If black holes destroy information, then their entropy should be infinite. But Bekenstein argued that this cannot be. Instead, he proposed that a black hole has finite entropy, proportional not to its volume, but to the area of its horizon. This was shocking. Entropy had always been associated with the bulk of matter, not its surface. But Bekenstein's idea hinted at something profound. The surface of a black hole encodes its information, as if the horizon were pixelated with bits. Soon after, Stephen Hawking deepened the paradox. Using quantum field theory in curved spacetime, he showed that black holes are not completely black. They radiate particles, a faint glow now called Hawking radiation. This radiation arises from quantum fluctuations near the horizon, where pairs of particles are created, one falling in, the other escaping. Over time, the black hole loses mass and eventually evaporates. But Hawking's calculations showed that the radiation is purely thermal, carrying no information about the matter that formed the black hole. If true, this would mean that information is destroyed, a direct violation of quantum mechanics, which insists that information is never lost. The clash between relativity and quantum theory reached its most dramatic form, the black hole information paradox. The paradox sharpened the idea that space-time may be pixelated. If a black hole has finite entropy proportional to its horizon area, then the horizon must contain a finite number of microscopic states. Each patch of area, roughly the size of a Planck square, may encode one bit of information. A black hole of solar mass would then have on the order of 10 to the power of 77 bits, an enormous but finite number. This is the holographic principle in action. The information content of a region of space is proportional not to its volume, but to its surface area. In this way, black holes point directly to discreteness. A continuous space-time would allow infinite states. A pixelated space-time, built from finite bits, resolves the paradox. The implications are staggering. If the holographic principle is true, then the universe itself may be a hologram, with its information encoded on surfaces rather than volumes. The smooth fabric of relativity becomes a mirage of bits arranged on boundaries, each bit a pixel of space. The entropy of a black hole becomes the count of these pixels, the tally of space-time atoms. Black holes are then not only astrophysical objects, but windows into the fundamental structure of reality. They are cosmic laboratories, compressing matter and geometry to their limits, revealing the discreteness hidden beneath continuity. The paradox of Hawking radiation is as sharp as any in physics. On the one hand, quantum mechanics insists that information cannot be destroyed. On the other, Hawking's calculation shows that the radiation from a black hole is purely thermal, carrying no trace of the details that formed it. If the black hole evaporates completely, the information is gone forever. This outcome would not just violate a minor principle, it would shatter the foundation of quantum theory, undermining the conservation of probability itself. Physics would unravel. To accept it would be to accept that the universe forgets, that events can occur without leaving a trace, that reality itself is not consistent. The tension between relativity and quantum theory sharpened with this discovery. Relativity permits the horizon to act as a one-way membrane, swallowing information without return. Quantum mechanics insists that every process, no matter how complex, must be reversible in principle. When these two principles collide in black holes, neither can be sacrificed. The clash forces a deeper resolution. Somewhere, beneath the illusion of smoothness, lies the mechanism that preserves information. Many physicists now believe that the key lies in pixelation, that the horizon is not smooth but composed of Planck-scale patches, each carrying bits of information that can be scrambled, transformed, and re-emitted, but never destroyed. This vision transforms our picture of black holes. They are not bottomless pits, but cosmic computers, processing information at the ultimate limits of physics. The bits on their horizons store data about everything that has fallen in, and the Hawking radiation, though thermal in appearance, may carry subtle correlations encoding that data. To detect these correlations is nearly impossible, as the radiation is faint and the correlations vanishingly small. Yet in principle, they must exist. If they do, then the black hole paradox dissolves and quantum mechanics survives. The smoothness of the horizon is then only an illusion. Beneath it lies a pixelated screen of information, flickering with the bits of space-time itself. The holographic principle extends this insight beyond black holes. If the information content of a black hole is proportional to its surface, then perhaps the same is true of any region of space. The number of states in a volume is determined by its boundary area, not by its bulk. This is shocking, because it contradicts the intuition that the more space you have, the more information you can store. Instead, the universe behaves as though its information is written on walls, not in interiors. The three-dimensional world we see may be a projection of two-dimensional data. In this sense, the black hole is not exceptional, but typical. Every region of space may be a hologram, every horizon a screen of pixels, every bit a Planck square on the surface. These ideas have found mathematical support in the holographic dualities discovered in string theory, such as A, D, S, C, F, T. In these dualities, a quantum theory without gravity living on a boundary is equivalent to a gravitational theory in a higher dimensional bulk. This equivalence suggests that spacetime itself can be reconstructed from information encoded on surfaces. The smoothness of geometry emerges from the entanglement of quantum states, and black hole entropy is simply the measure of this entanglement. Continuity is not fundamental. Pixelation is not optional. It is the only way to reconcile relativity and quantum mechanics. But the details remain mysterious. How exactly is the information stored on the horizon? How is it released in radiation? Does it scramble instantly, as some models suggest, or does it leak slowly, hidden in correlations? Is the interior of a black hole real, or is it only an emergent illusion encoded in the horizon's pixels? These questions drive some of the most intense debates in modern physics. The firewall paradox, for example, asks whether the horizon is smooth, as relativity predicts, or searing with quantum fire, as some interpretations of information preservation require. Each proposal carries radical consequences, and none are settled. What is clear is that black holes are no longer just astrophysical oddities. They are arenas where the deepest questions of space-time are fought. In this way, black holes become windows into pixelation. Their entropy points to finite bits of space-time. Their radiation demands a mechanism of information preservation. Their paradoxes force us to abandon the illusion of smoothness. To study them is to study the atoms of geometry themselves, to glimpse the Planck scale not through colliders, but through the cosmos. Black holes, born from collapse and hidden behind horizons, may hold the clearest evidence that spacetime is not continuous, but built from pixels of area, finite and countable. Black holes, once imagined as cosmic dead ends, have become the brightest beacons pointing toward the discreteness of spacetime. They compress matter to extremes, hide information behind horizons, and evaporate in a glow of radiation. In doing so, they expose the limits of relativity and demand the precision of quantum theory. They tell us that smoothness cannot be real, that information cannot be infinite, and that the horizon is not a featureless veil, but a screen of pixels encoding the states of spacetime. Each Planck-sized patch of area is a bit, a piece of the cosmic code. The black hole is not a mystery of destruction, but a revelation of discreteness. The information paradox has not yet been fully solved, but its very existence has reshaped our understanding. Most physicists now agree that information is not destroyed. Somehow, the details of everything that falls into a black hole are preserved and eventually released, perhaps scrambled, perhaps disguised, but never lost. This is the mandate of quantum mechanics, and it cannot be broken. The question is not whether information survives, but how. The holographic principle suggests that the horizon holds the key, storing data in its pixelated surface. String theory supports this, showing that black hole entropy can be derived from counting the microscopic states of strings. Loop quantum gravity supports it as well, describing the horizon as stitched from loops, each carrying finite states. In both visions, the message is the same. Black holes are not smooth, they are pixelated. This changes how we think of the universe itself. If black holes encode information on their surfaces, then perhaps all of spacetime does the same. If the number of states is finite, then spacetime cannot be continuous. It must be quantized, emergent, or both. The information paradox is not only about black holes, it is about reality. The cosmos may be a hologram, its smoothness an emergent illusion, its information stored in finite bits on surfaces that define regions. What began as a puzzle about collapsing stars becomes a clue to the structure of existence. The paradox also reveals the unity of physics. General relativity, quantum mechanics, thermodynamics, and information theory converge on black holes. Their entropy is thermodynamic. Their radiation is quantum. Their horizons are geometric. Their paradoxes are informational. Black holes are not just astrophysical objects. They are crossroads where all fundamental theories meet. At those crossroads, the illusion of continuity shatters, replaced by hints of discreteness. The atoms of spacetime reveal themselves not in laboratories but in the skies, in the collapse of stars and the evaporation of horizons. The cosmos itself has already run the experiment for us. Our task is to understand its results. As this chapter closes, the story turns outward. From black holes we learn that spacetime must be pixelated, that surfaces encode information, that horizons are not smooth but stitched from finite bits. The next step is to ask what this means for reality as a whole. If space is pixelated, how does it affect causality, relativity, and the flow of time? If information is encoded on surfaces, how does the universe preserve its meaning? If continuity is an illusion, what replaces it? These questions lead us to the broader implications of discreteness, beyond black holes, beyond singularities, into the nature of reality itself. Up to this point, the journey has been a search for clues. We have traced the illusion of continuity from the smooth geometries of relativity to the quantum hints of discreteness at the Planck scale. We have explored loop quantum gravity, which weaves space from loops, and string theory, which sings space-time from vibrations. We have considered Wheeler's foam, jittering at the smallest scales, and we have examined the paradoxes of black holes, which encode information on surfaces rather than volumes. Each path, though different, points toward the same possibility. Space and time may not be continuous. They may be pixelated. But if this is true, what does it mean for the universe we live in? What changes when the stage itself is made of atoms? The first implication is profound. If space is pixelated, then relativity, the theory that says the laws of physics are the same for all observers, may only be approximate. Relativity assumes that space-time is smooth, that no observer can detect an absolute rest frame or a preferred direction. But a pixelated universe may not preserve this symmetry perfectly. Just as a digital photograph looks smooth until you zoom in and see the pixels, a pixelated spacetime may look symmetric until you probe close to the Planck scale. At that point, small violations of Lorentz invariance, the core symmetry of relativity, may appear. Particles of different energies may not move in exactly the same way. High-energy photons may drift apart from lower-energy ones. Cosmic rays may scatter differently depending on their direction. These deviations would be tiny, hidden at ordinary scales, but they could accumulate across cosmic distances. To detect them would be to detect the pixels of reality. The second implication lies in causality, the principle that events unfold in a definite order. In continuous spacetime, causality is protected by the smooth geometry of light cones, which define what can influence what. But in a pixelated universe, the edges of light cones may blur. Events may no longer be sharply ordered. The smallest ticks of time may not line up neatly, but jitter with uncertainty. This does not mean that causality breaks down completely. At large scales, the averaging of countless pixels restores the familiar order of cause and effect. But at the Planck scale, the clarity may dissolve. The very notion of before and after may become ambiguous. Time may not flow as a river, but as a sequence of frames, like the flickering of a film. Between frames, nothing happens. Reality updates in discrete ticks, and causality emerges as an approximation. A pixelated spacetime may also offer explanations for some of the universe's greatest mysteries. Dark energy, the force driving cosmic acceleration, might be a manifestation of discreteness. The energy of spacetime pixels could act as a cosmological constant, pushing the universe apart. The structure of the early cosmos, with its tiny fluctuations that seeded galaxies, may also trace back to pixelation. If space is discrete, then the inflationary era could have amplified its grain, leaving imprints in the cosmic microwave background. Even the ultimate fate of the universe may depend on whether space is continuous or pixelated. If continuity is an illusion, then the cosmos is finite in its information content. Its story cannot be written in infinite detail, but only in the finite language of pixels. If space is pixelated, then determinism itself may be called into question. In a continuous universe, the equations of physics allow, at least in principle, the exact prediction of the future from the present. Given initial conditions and precise laws, the cosmos unfolds with perfect inevitability. But in a pixelated universe, the very concept of exactness may fail. If distances and times are quantized, then initial conditions cannot be infinitely sharp. They can only be specified in discrete steps, in units of the Planck scale. This introduces a fundamental grain of uncertainty, one that is not simply the uncertainty of quantum mechanics, but the uncertainty of geometry itself. The future is no longer perfectly determined, because the stage upon which events play out is not continuous, but discrete. This does not mean chaos. Just as quantum mechanics does not abandon order, but replaces certainty with probability, so too would pixelated space-time replace determinism with patterns of emergence. The broad strokes of physics would remain reliable. Galaxies would form, stars would shine, planets would orbit. But beneath these macroscopic truths, the details would shimmer with indeterminacy, born not only of quantum probabilities, but of the finite granularity of the cosmos itself. Continuity would be revealed as an approximation, and determinism as an illusion of scale. The relativity of Einstein also faces revision in a pixelated universe. Relativity insists that no observer can detect absolute motion, that the speed of light is the same for all. This symmetry depends on the smoothness of space-time, which allows transformations between frames without residue. But discreteness may break this symmetry, if only slightly. At the Planck scale, the lattice of pixels may define a preferred frame, a hidden scaffolding beneath the illusion of symmetry. High-energy particles might betray this frame, their paths subtly distorted, their speeds deviating from light by infinitesimal margins. Lorentz invariance, sacred for over a century, might prove to be a grand approximation, surviving at all scales we have tested, but dissolving at the deepest level. The symmetry of relativity would then be like the smoothness of a sphere carved from grains of sand, exact to the eye, but granular beneath. Such a revision does not destroy relativity, but places it within a larger framework. The beauty of Einstein's equations remains, but they are recognized as effective descriptions, not ultimate truths. At scales where space-time pixels are invisible, relativity reigns. At the Planck scale, discreteness asserts itself, and new laws govern. This layered reality mirrors the history of physics. Newton's laws were not false, but incomplete, absorbed into relativity and quantum mechanics. Relativity itself may not be false, but incomplete, absorbed into a theory where space and time are quantized. The illusion of continuity, defended so long, would give way to the recognition of discreteness as the deeper truth. The possibility of pixelated spacetime also reshapes the question of natural laws. In a continuous universe, laws are written on an infinite canvas. precise to arbitrary scales. In a pixelated universe, laws must respect the grain of geometry. Equations cannot demand more precision than the lattice allows. Symmetries cannot extend beyond the limits of pixels. Conservation laws may themselves emerge from the finite architecture of space. Physics becomes not the story of continuous fields, but the story of discrete patterns, woven from the atoms of geometry. The ultimate laws of nature may not be equations at all, but codes, algorithms governing how pixels update from one moment to the next. Reality itself may be computation, with space-time as its hardware and physics as its software. In this way, the pixelation of space-time is not a mere technical adjustment. It is a transformation of worldview. Determinism becomes approximation. Relativity becomes emergent. Laws become algorithms. Continuity becomes illusion. The cosmos, once imagined as a smooth and infinite fabric, becomes finite, quantized, and coded. And yet, far from diminishing its majesty, this transformation enriches it. The universe becomes a mosaic, each pixel a piece of a grand design, each bit of geometry a note in the cosmic symphony. To live in such a universe is to live within a masterpiece of discreteness, a reality whose smoothness is the shimmer of countless pixels seen from afar. A pixelated universe may also cast new light on the great puzzles of cosmology. Dark energy, the mysterious force that accelerates the expansion of the cosmos, has long resisted explanation. In a continuous space-time, vacuum energy leads to infinities that defy observation. But in a pixelated universe, the vacuum cannot store infinite energy. Each pixel has a finite capacity, and the sum across the cosmos may yield a small but non-zero value, precisely the scale we observe as dark energy. In this way, discreteness may not only resolve infinities, but also explain the acceleration of the universe itself. The expansion becomes not a mystery, but a consequence of the finite grain of space. The earliest moments of the universe also reveal the fingerprints of pixelation. The cosmic microwave background, the faint afterglow of the Big Bang, carries patterns of fluctuations imprinted when the universe was young. These fluctuations seeded the galaxies and clusters we see today. Their origin is usually attributed to quantum fluctuations stretched by inflation, but if space-time is discrete, then the very grain of geometry may have left an imprint. Tiny irregularities in the lattice of pixels could have been amplified, etched forever into the background radiation. To read these patterns with greater precision is to read the script of discreteness written across the sky. The universe itself becomes a fossil, preserving the memory of its pixelated birth. Even the ultimate fate of the universe is touched by this vision. In a continuous cosmos, the story is open-ended, with infinities stretching into the future. But in a pixelated cosmos, the number of states is finite. The universe has a finite information content, bounded by the number of pixels on its horizons. Its history is not infinitely detailed, but finitely coded. This means that the story of the cosmos, though vast, is written in a countable script. The future is not endless in possibilities, but constrained by the architecture of space-time itself. In a sense, the universe is not a boundless canvas, but a completed mosaic, each tile already determined by the structure of its pixels. Yet the most profound implication of pixelation is philosophical. Continuity has been our assumption since the birth of geometry, the premise of calculus, the stage of relativity. To abandon it is to abandon a worldview that has lasted for millennia. But physics teaches us that illusions often masquerade as truths. The solidity of matter was an illusion, shattered by atoms. The certainty of determinism was an illusion, shattered by quantum mechanics. The smoothness of space-time may be the next illusion, shattered by the recognition of pixels. Reality, it seems, is not infinite, but finite, not continuous, but discrete, not smooth, but quantized. And yet, in its discreteness lies its majesty, for from finite pixels arises the infinite beauty of the cosmos we see. As this chapter ends, we stand before the most fundamental question. If space is pixelated, then causality, relativity, and determinism are not ultimate but emergent. Dark energy, the early universe, and the fate of the cosmos are not mysteries but consequences of discreteness. The universe is not a canvas but a mosaic. But is this vision true? Or is continuity still the bedrock of reality, and discreteness only an illusion of our theories? The next step is to return to the question in its broadest form. Is reality continuous, or is it pixelated? The future of space-time depends on the answer. The story of space-time is one of evolving illusions. For the ancients, space was a stage of absolute stillness, an infinite backdrop upon which the planets moved. For Newton, it became the theatre of motion, continuous and eternal. For Einstein, it bent and curved, dynamic and alive, shaping the flow of time and the dance of matter. For quantum mechanics, it was the silent arena where uncertainty played out, smooth and unquestioned. But the deeper we look, the more the illusion wavers. The Planck scale reveals hints of discreteness. Loop quantum gravity weaves geometry from loops. String theory sings space-time from vibrations. Wheeler imagines foam bubbling at the smallest scales. Black holes encode information on their horizons. Everywhere, smoothness is challenged. Everywhere, continuity begins to dissolve. The future of space-time depends on how these visions converge. Loop quantum gravity shows that areas and volumes can be quantized, resolving singularities and replacing the Big Bang with a cosmic bounce. String theory suggests that space-time itself is emergent, that the smooth geometry we inhabit is a projection of deeper vibrations and entanglement. Quantum foam demands that geometry fluctuate violently at the smallest scales, refusing to remain calm. Black holes tell us that horizons carry finite pixels of information, and that volume is an illusion born of surfaces. Each path is different, but all point toward the same destination. Space-time is not continuous. Its smoothness is an illusion, a shimmering surface concealing discreteness or emergence beneath. The experimental frontier has not yet pierced this illusion, but it has sharpened the boundaries of possibility. Gamma-ray bursts reveal no dispersion across billions of light years, yet their silence speaks. Gravitational waves ripple with perfect fidelity, yet their smoothness is a clue. Cosmic rays and neutrinos arrive intact, yet their survival sets strict limits on foam. Even the holometer, whispering with lasers, reported no noise, yet in its silence, it mapped the possibilities of holographic pixelation. The instruments of today cannot yet see the pixels of space, but they prepare the way. The instruments of tomorrow may do more. The search is not over. It is only beginning. If space-time is pixelated, the implications reach beyond physics into philosophy. Continuity, once the bedrock of thought, would be revealed as an illusion. Causality, relativity, determinism, all would be emergent. The laws of nature themselves would be rewritten as codes, algorithms running on the hardware of space-time pixels. The universe would no longer be a canvas, but a mosaic, no longer infinite in detail, but finite in its information. This would not diminish its grandeur. It would enrich it, revealing a cosmos built from finite pieces, yet capable of infinite beauty. The illusion of smoothness would be replaced by the wonder of discreteness, the awe of a reality woven from atoms of geometry. And yet, the question remains unsettled. No experiment has revealed the pixels of space. No theory has gained universal acceptance. Relativity still reigns at large scales, and quantum mechanics still rules the small. The union between them remains elusive, hidden behind the illusion of continuity. The future of space-time will be decided not by speculation alone, but by observation, not by elegance alone, but by evidence. The cosmos will reveal its truth when instruments grow sharp enough, when black holes are probed deeply enough, when the early universe is read clearly enough. Until then, the illusion endures. The future of space-time may not belong to a single theory, but to the merging of many. Each vision reveals a different facet of the same mystery. Loop quantum gravity shows us that space can be chopped into quanta of area and volume, that singularities can be softened into bounces, that horizons can be counted bit by bit. String theory shows us that particles are not points but vibrations, that space-time itself may not be fundamental but emergent, that the holographic principle encodes volume on boundaries. Wheeler's foam shows us that geometry cannot remain smooth at the Planck scale, that fluctuations must bubble and boil, that space-time is restless at its core. Black holes reveal that information is not lost but stored in finite pixels, that horizons are screens of bits, that surfaces are more fundamental than interiors. Each path contradicts the illusion of smoothness, but in different ways. Loop quantum gravity denies continuity by quantizing geometry directly. String theory denies it by replacing geometry with harmony and emergence. Foam denies it by insisting on fluctuations, jitter, and turbulence. Holography denies it by encoding information on surfaces rather than volumes. None of these visions has yet been proven, but together they form a chorus, each voice distinct, yet all singing the same refrain. Continuity is not the final truth. Beneath the smoothness lies something discrete, something emergent, something more fundamental than geometry itself. The task of the next century is to weave these voices together. Perhaps loop quantum gravity and string theory are not rivals, but complements, describing different aspects of the same deeper structure. Perhaps foam is the microscopic face of loops, or the flicker of vibrating strings. Perhaps holography is not a metaphor, but the principle that binds all together. The rule that ensures information is preserved in a universe of finite bits. The future may reveal that each vision is partial, that the truth is a synthesis, a theory of quantum gravity that unites discreteness, emergence, and information into one framework. To find that framework, physicists are turning to new mathematics, new experiments, new ways of imagining. Entanglement is emerging as the bridge, the quantum connection that may build space-time itself. The fabric of geometry may be nothing more than the network of entanglement, stitched together like a web, dense enough to appear continuous. Black hole thermodynamics provides another guide, showing that entropy scales with area and that horizons carry the secret of space-time's atoms. Cosmology provides yet another, pointing to the imprints of pixelation in the early universe and the role of discreteness in dark energy. Each clue, though incomplete, is a step toward the mosaic of truth. For now, we live in the tension between illusion and reality. Our instruments measure smoothness, but our theories demand discreteness. Our equations describe continuity, but our paradoxes reveal its failure. This tension is not failure. It is the frontier. It is the mark of progress. Every revolution in physics begins with such tension, when theory and observation pull apart, when old assumptions crumble under new paradoxes. The illusion of continuity is strong, but no illusion lasts forever. The day will come when the pixels of space-time are revealed, whether as loops, strings, foam, holograms, or something beyond imagination. The fate of physics may rest on the answer to a single question. Is reality continuous, or is it pixelated? For millennia, we believed in smoothness, in infinite divisibility, in a stage that could be cut forever without end. Our mathematics, our geometry, our equations of motion all grew from that faith. But now the evidence gathers, the paradoxes mount, and the visions converge. Everywhere we look, continuity falters. Atoms shattered the illusion of continuous matter. Quanta shattered the illusion of continuous energy. Now, space-time itself trembles under scrutiny. The illusion of smoothness may be the last to fall, and the fall may reveal a cosmos woven from finite threads. If space is pixelated, the universe is not an infinite canvas, but a finite mosaic. Each pixel is a Planck-length square, each tick of time a Planck's second beat. Together, they weave the fabric of reality, dense enough to appear smooth, but finite in number, finite in detail. Black holes confirm it by encoding information in bits of area. The holographic principle confirms it by placing information on boundaries. Loop quantum gravity confirms it by quantizing areas and volumes. String theory confirms it by showing that space-time itself is emergent. The chorus of physics sings in harmony, even if the words differ. The message is clear. Continuity is not fundamental. The universe is finite in its architecture, infinite only in its beauty. And yet, there is wonder in this finitude. A mosaic is not less than a canvas. It is more. From finite tiles arises infinite variety. From discrete notes arises endless music. From Planck-scale pixels arises galaxies, stars, life, and thought. The majesty of the cosmos is not diminished by discreteness. It is enriched. To know that the smoothness of space-time is an illusion is not to lose awe, but to gain deeper awe, to see beneath the surface, into the code of reality itself. The atoms of geometry are the alphabet of existence, and the universe is the story they write. As we close this journey, the final words belong not to equations, but to vision. If space is pixelated, then the universe is not a boundless canvas painted with continuous strokes. It is a cosmic mosaic, painted one quantum at a time. Each pixel is a brushstroke of geometry, each bit a thread of meaning, each Planck scale tick a heartbeat of reality. To live in such a universe is to live inside a masterpiece, a finite structure that gives rise to infinite wonder. And whether continuity is real or pixelation is true, the search itself is the proof of our curiosity, the sign that we too are part of the mosaic.